Sir, good morning.
Good morning, Suresh. Sugala.
Sugandana, sir.
Good morning, Professor Joseph.
Good morning.
Morning.
Ajit. We meet once a year for the workshop. Last year also you were.
Yeah, that's right. Yeah. Good morning to everybody.
Yeah. Good morning.
Good morning.
Sir.
Good morning.
Good morning, Sajid.
Good morning, sir.
Yeah, so we meet once a year. Sajid and I meet once a day at least.
Good morning, sir. Good morning, Babu sir and Ajit sir.
Good morning. Sure.
Are you hearing me well, sir, right?
Yes. I'm hearing. Yeah.
Your voice is a little bit broken.
Yes, Dr. Shaji join ചെയ്തിട്ടുണ്ടോ?
Hello.
Shaji.
Sir.
Hello. Good morning.
Good morning, Shaji.
Good morning. Suresh.
Yeah. Good morning, teacher.
Good morning, sir.
Good morning.
Good morning.
Good morning.
Good morning. Good morning.
Good morning, teacher.
Morning, teacher. Good morning.
Shall we start or wait for 2 more minutes? 3 participants. A very warm good morning to one and all, and hearty welcome to the webinar on astrophysics and cosmology, which is organized as a tribute to our dear Professor V.C. Kuriakose, famous physicist and former head of the Department of Physics, Cochin University of Science and Technology, who left us all on the same date, 30th August 2018. This workshop is the third memorial event in Professor V.C. Kuriakose Memorial Workshop Series, organized by Astronomical Society of Kerala in collaboration with Inter-University Center for Astronomy and Astrophysics, Pune. Professor V.C. Kuriakose was the mentor for generations of astronomers from Kerala. Kuriakose sir guided 22 researchers towards their doctoral degree. In his scientific career, Sir made important contributions to several fields, including gravitation and cosmology, astrophysics, and nonlinear dynamics. He had more than 155 publications in high impact factor journals. Professor V.C. Kuriakose was active in the dissemination of astronomy and astrophysics among the young generations. Sir was very active in the field of research and also in the promotion of astronomy in Kerala, for which he formed a group called Astronomical Society of Kerala, ASK. VCK sir guided the group and conducted regular sky watches and classes at schools and colleges at several places in Kerala. Until his last breath, Kuriakose sir relentlessly worked for the cause of astronomy education in universities in our state and in the country. Even after the retirement, our sir tried his level best to motivate more students and encourage them to learn astronomy and astrophysics. That's why we thought such a workshop series is the most suitable tribute for our Kuriakose sir. First of all, let me invite Professor P.K. Suresh from University of Hyderabad for the formal welcome speech.
Thank you. Very good morning to all, and good afternoon to some people other part of the globe, and good evening to some other people other part of the globe. We all gathered through online mode today to mark our tribute to great teacher, wonderful human being, and former head of the department, Professor V.C. Kuriakose sir. Today is Remembrance Day. The Remembrance Day is not just remembering a single day. So this is again a chance to recollect his contribution to his research field, teaching, other things. As Dr. Minu Joy pointed out, Professor Kuriakose sir was very much interested spreading astronomy and other population science, especially in Kerala. Therefore, students of Professor Kuriakose sir and his other friends and colleagues thought to give a better tribute. Professor Kuriakose sir is to arrange workshop or serious seminar beneficial to students in Kerala. So in this series, this is the third series of the workshop. So this workshop today is going to inaugurate by an eminent person, another great teacher, and supervisor was Professor VCK Memorial sir, and the colleagues, Professor Babu K. Joseph sir, former Vice Chancellor of Cochin University of Science and Technology. I need not to say an introduction to all of you, Professor Babu Joseph sir. So I welcome you, sir, with a great pride, and GSM, I welcome you, sir, very cordially and hearty welcome to this workshop, sir. We have this workshop, there are two talks. First talk will be given by Professor Ajit Kambave, a well-renowned scientist, and he was a former director of IUK Pune. Ajit Kambave is also very much interested in popularizing astronomy in India. Some of us are known to us. So he's another right person to give a talk in this kind of workshop. So I welcome you, sir, with a great pride, and I welcome you to a warm welcome to this workshop. And we all of you know that in July we lost a very world-renowned scientist. We lost a world-renowned scientist in July. So that scientist remembrance we can also give another tribute by organizing another tribute lecture. Professor Weinberg lost in July. Therefore, we thought we'll arrange a talk in remembrance of Professor Weinberg. Dr. Shaji agreed to kindly give a talk on some contribution made by so Shaji is a right person. He is very much interested in popularizing science in Kerala. Therefore, I also welcome Dr. Shaji to this workshop, and a very special welcome to Dr. Lolam teacher and Professor Vireko sir, families and friends. I also welcome the teachers of Cochin University of Science and Technology, especially Professor VCK Memorial sir, colleagues and other people. And I also welcome some of the IUK associates, and also I welcome the participants of this conference. I also welcome once and all for all again. Thank you. Yeah, I'll leave to Minu.
Thank you, Dr. Suresh. Now let me invite Professor K. Babu Joseph for the inauguration of the workshop and the memorial speech. Over to you, Babu sir.
ബൗസാറിന്റെ മൈക്ക് മ്യൂട്ടഡ് ആണ്.
Thank you, Minu. Today we are observing the third anniversary of Professor VCK Memorial's demise. On this occasion, the students and admirers of Kuriakos have organized a workshop, and I understand that this is the third of its kind. Workshop is on gravitation cosmology, astronomy and astrophysics. It will be fitting on my part to recall some stories in which both Kuriakos and I were the characters. As mentioned here, I met Kuriakos at UC College as a student in the special BSc program. Special BSc and ordinary BSc, there were two branches of BSc available in those days, in the 60s, late 60s. I happened to join there as a faculty before I joined USAT. Well, Kuriakos was one of my students there. And from that time onwards, there started a very intimate association with you. I don't want to repeat the detailed story because I have already told it on earlier occasions. But one aspect which I think is not receiving sufficient attention by the organizers of workshops like this is that Kuriakose started his career as a high energy physicist, especially quantum field theory. His PhD work is on quantum fields at high temperatures. It was a very popular branch of quantum field theory in the 70s, late 70s and 80s. There is another reason why I am mentioning this because Steven Weinberg is one of the creators of quantum field theory at finite temperatures. Roman Jacques, Steven Weinberg, and others developed this aspect of quantum field theory for the first time. We were among those who jumped to the bandwagon of field theory at finite temperature. Kuriakose and I started working on it from early days when he joined for his PhD under my guidance. Well, our first task was to decipher the remarkable papers by Weinberg and others in this field. That we did, and Kuriakose was progressing well with his work on quantum field theory at finite temperatures. I got a chance to visit University of Texas at Austin when he was preparing his thesis. So naturally I met Weinberg there. He was a very jovial, friendly person. So it was easy for me to meet him. There was no ceremony in getting permission to meet him. Simply knock on his door and enter. He would keep his door open. So anybody is welcome. So I happened to meet him in his room more than one occasion, 2 or 3 times. I happened to be in the same lift several times. Of course, he was not alone in the lift. He will be always surrounded by his students and colleagues. And one remarkable thing about him is that once I noticed him sitting in a seminar, attending a talk on cosmology by James Hartle. James Hartle, many of you know, was famous for his work on the wave function of the universe and quantum cosmology. So he was explaining some aspects of that. I noticed that Weinberg sleeping in the front row. He was sitting there with eyes closed. And I thought he was sleeping. When Hartle was finished, Weinberg raised his hand with questions. So there was a shower of questions from side, and there ensued a very lively discussion. So that was one thing that I remember of him. Whenever somebody mentions his name, immediately I am reminded of the casual, apparently casual and careless manner in which Weinberg used to sit in seminars and workshops. Well, his colleagues, among his colleagues were Wheeler, John Wheeler, Sudarshan, Professor C. Sudarshan, and others. Well, some of his colleagues happen to be my collaborators on a project. I don't want to go into the details. All of them, without an exception, were of very high opinion about Weinberg as a person. Of course, there is no second opinion about his competence as a scientist. All would agree on that. But as a person, many great scientists, so-called great scientists, are known to be not so good in their best professions. Weinberg was. I explained to him the work Kuriakose and I were doing. At that time, we were working on variation of coupling constants, that is, forces with temperature. We studied the lambda 5-4 model. We could derive an expression for the dependence of the party coupling constant. So I explained to him all these things, and he showed great interest. He asked me to go ahead with that kind of work. In that department, I had two collaborators. All of us were working on project on van der Waals forces, behavior of van der Waals forces. So I could complete it. That is that. Well, coming back to Kuriakose, he lived a full life. He trained more than 50 such scholars, more than 150 such papers he has published. He has contributed to the development of theoretical physics in the States very much. His signal contribution is the starting of research on black holes. He was the first person to inaugurate the study of black holes in Kerala. Many of his students have worked on different aspects of black holes, thermodynamic properties, quasi-normal modes. So, yesterday I was discussing these things with one of his students, Dr. Taran. We foresee a great potential for the ideas he and his students contributed to this aspect of black holes. Now that the merger of black holes is being studied vigorously and intensely, I hope that the contributions of Kuriakose and his students will be followed by several schools of systems across the world. Well, first, people observed the merger of two black holes. Even that phase is not studied from Kuriakose's point of view. What are, for example, what are the quasi-normal modes when merger takes place? The resulting configuration will have a different set of different from those of the original individual platforms and things like that. Now, the merger of three platforms, again, same problems, thermodynamic problems. I wonder whether the end of the world is going to be like that. We are probably part of a very huge, supermassive black hole. Somewhere, our universe, nothing. And the what reality is going to end like through merger of black holes. It's only speculation. There may not be any physical justification for that. One argument counter to it is that does thermodynamics allow this type of phenomenon? That is, when the merger takes place, there is change in symmetry, geometrical symmetry. There is deviation from asymmetry to symmetry, transition to spherical symmetry. That is more order. Is it allowed thermodynamics? Is not the second law of thermodynamics against it? What is its significance? What is it? I think these are questions which may or may not be relevant at all. But anyway, Kyriakos' name will be remembered as a pioneer in black hole physics in this part of. With these words, I inaugurate the workshop on gravitational cosmology and astrophysics. I offer a special welcome to my old friend, Professor Ajit Kampavi. I welcome Dr. Shaji also to speak about Weinberg's contributions. Thank you.
Thank you very much, dear Babu sir, for the words from your heart and for inaugurating the event. Next, we will have the first session by Professor Ajit Kembave. Let me invite Dr. Ravi Kumar CD from Calicut University to introduce Professor Ajit and to chair the session.
Good morning. Am I audible?
Yes, Ravi, yes.
Yeah, okay. Good morning to you all. As we have been listening, it's a somber day today that we find it difficult to reconcile with the demise of Dr. Kyriakos, former professor and head, Department of Physics, Cochin University of Science and Technology, who departed us on this day 3 years back. Through his commitment to education and research, his care for his students, and above all, the love that flowed unhindered, we, his students, stand before you, all feeling the gratitude towards our teacher. On this occasion, I stand humbled and privileged to invite Professor Ajit Kembave, Principal Investigator, Pune Knowledge Cluster, Emeritus Professor, and former Director of IUCA Pune, to the first session today. It's indeed very pleasing to see you online, at least, Ajit, in this pandemic situation. Let's hope COVID can stay away so that we can have our regular meetings sooner. With these words, I once again invite Professor Ajit Kembave to deliver his talk on Pune Knowledge Cluster and Citizen Science Astronomy. Over to you, Ajit, please.
So thank you very much, Ravi. Like Ravi says, that this is both a somber and a joyful occasion. It's somber because our friend Kyriakos is not with us any longer. We are reminded of that on this day every year. But it is joyful because we are celebrating his life. Because he had such a very simple, very humble person. But he did so much for so many. I also wish to compliment Lilama teacher again for all that she has done also for teaching in Kerala. And then Ravi is a bridge between Kuriakose and myself because he was one of the students that Professor Kuriakose directed towards me. I had a very long and very fruitful association with him. Um, and one of his amazing qualities was that he was silent most of the time. Okay, and yet he used to convey so much. And I was very excitable when I was much younger, and quite often I used to get very angry and shout at him. And the more I shouted, the more silent he became. So quite quickly, a good equilibrium was established. I learned so much from him, and I'm very happy to be giving this talk. Now, as some of you know, but not many, I've been involved for the last 1 year. It is actually 1 year and 25 days in a project called the Pune Knowledge Cluster. Now, some years ago, my friend Arun Grover, and he and I grew up together from the age of 20. He was the Vice Chancellor of Punjab University. Punjab, Chandigarh, and Mohali have a large number of educational institutes, and so what he did was that he started something called a cluster there and set up a program by which people from different institutes could work with each other. I was very impressed with that. And I made a suggestion that that should be done. And my friend Professor L.S. Shashidhara, who is a very distinguished biologist. He's far younger than me, but he's a distinguished biologist, and he used to work in ISER Pune. Now he continues to be there, but much of his work is now based in Ashoka University in Delhi. So he and I spoke to Professor Vijay Raghavan, who is the principal scientific advisor now, and he liked the idea very much. Then we wrote down the proposal. But before a proposal could be implemented, what happened was that it got mentioned in certain circles in Delhi. And so then it became accepted as a very major idea. And so the government decided that they should set up clusters, not for the very narrow view we had at the time of bringing academic institutes together, but to tie up academic institutes, R&D organizations, and the industry to do something good for the city. So then the government also decided that there will be clusters in several places. So now presently we have clusters in Delhi, Hyderabad, Jodhpur, Pune, and Bangalore. And there are many more clusters which are in the making. So it turned out that these are pretty exciting ideas. And they have been some of the clusters have been very productive. Completely new concepts have been derived. And the only problem is that it requires work at the rate of about 28 hours per day and 8 days a week, which is very difficult to do. So but I thought that this concept is quite important and it should be brought to the notice of people. And I negotiated with Sajid and Joe, okay, saying that they'll allow me to talk about non-astronomical matters, providing there is also an astronomical component in it. Okay, so as it happens that there's 5% of the cluster work is on astronomy, and I'll mention that, and that has suddenly become very, very exciting. Please excuse me, I'll be back in one moment to change my specs. I'm sorry, I forgot to change my specs. So I'll describe to you a little bit about the cluster, and then invite you to join us in our efforts, and in fact start your own cluster. But there's one thing which is common between Maharashtra and Kerala right at the moment, and that is COVID-19. Okay, so you see that between us, we are contributing about 80% of the number of cases in the country. Even though the number of cases actually reported may be much smaller, much larger than what we think it is, but still our two states are really they stand out as major contributors. And so therefore, we must all, as scientists, try to do something to mitigate this situation. We have been doing a little bit of work in Pune on this one, this COVID matter, which also I'll be describing today. And I've been talking to Sajid about it from time to time. So let me put on share my thing. Do you see my screen?
Yes, yes.
Yeah, okay, great. And so if the slides don't move, please let me know.
Yeah.
Okay, yeah. All right, so this is a Pune knowledge cluster, and you see that there's a Pune fort, and then all kinds of high-tech things here with a tree, and that captures the ethos of our project. Like that, we have to bring science and technology to the game, and then it is established by the Office of the Principal Scientific Advisor, and it is currently administered by Ayuka. Right. So, what is our mandate? Our mandate is very simple, and it says that bring together academic and R&D institutions, industries, industry associations, NGOs, civic bodies, government to work for the good of the city of Pune and the surrounding regions using science and technology. So there are other clusters in other places which will be working for their own cities, but we are also all working together. And many of the efforts that we are making are actually scalable. Okay, meaning that they can be expanded in size, they can be easily adopted to other situations. And that is the requirement we are building into all our efforts. Right, then, so now we have, by definition, we need partners. The day before yesterday, for example, we had the second meeting of our advisory committee. Our advisory committee is very distinguished. Professor Dr. R. A. Mashelkar, you might have heard about him. He is a very famous scientist. Used to be the Director General of the CSIR. He's the chair of the committee. And then there are academics and there are industrialists. And it sometimes I'm sometimes very find it strange to find the dollar billionaires on the committee. Okay, so because Pune is a small city and nearly everybody knows nearly everyone, and so it is quite easy to gather together people from different walks of life, and they're also obliging. So they do come to these meetings and they give us advice and so on. And one of the important advices that they give us is that we should not take up too much because we are a very small organization, but we have to persuade other people to do the work. Okay, so you see that here there's a lot of different organizations. They're all highly Pune based, so some of you may not have heard about them. For example, AFMC is the Armed Forces Medical College. DRT is the Defense Institute for Advanced Technology. Then we have got NCL, which many of you would have heard about, ISL Pune, Ayuka. Then there are the hospitals, right? And then there are then the university, Symbiosis, which I'm sure many of you are familiar with. There are computer companies like TCS and Persistent. Okay, and then we have with us also as very active partners different arms of the government. Because that is very important. Because if you are doing something for the city, you cannot do that without collaborating with the civic sector. So you got DET, which is the District Institute for Educational. Then you have the Maha Metro, the Maharashtra Metro Service, Pune Municipal Corporation, Pune Smart City Project, and the Zilla Parishad. Zilla Parishad is the district administration. And so you may wonder what we are going to do with them, but you will slowly find it as I describe the project. Right, so then our team is very small at the moment. So we are the director of Ayuka, and then Shashidhara and I are the PI and the co-PI. And then we have got 3 senior advisors. And those of you who have been associated with Ayuka for right from the beginning could recognize the name of Anita Kane. Actually, she and I set up the entire computer center of Ayuka. She left us after some years. She joined TCS and she was with them for a long time. And then TCS towards her superannuations, TCS placed her, as part of in the PMC, Pune Municipal Corporation, as the Chief Data Officer. Rashmi Urdhwareshe used to be the director of a place called the Automotive Research Association of India here, and which is one of the leading automotive organizations in the country. And she's working on sustainable mobility. Anita Khan is working on environment and health. Suresh Gaskabri is in the capacity building program. Then we have program managers, assistant program managers, several of whom are PhDs or they are otherwise very highly involved in their own program. And apart from that, we also have a number of people who work on projects. But this is a relatively small group, and we are carrying on. We are going to be located in the University of Pune, where there's a new building, and we have got one floor of that building to ourselves. It's a small area, and we expect to move into those offices in about a week's time. They are being furnished. You see, our entire 1 year period was in the lockdown. Okay, so because Pune has been effectively under the lockdown right from April of last year, and therefore all our operations were very difficult. We mainly meet remotely, and therefore we couldn't get our offices going, but now that has happened. In spite of that, the work is carried on. Okay, so now I come to what are our projects and programs. Right, so you have seen our mandate is work for the city of Pune, but one could do that in many different ways. So we have chosen certain number of ways to do so. Okay, so you see that here we have defined these verticals, right? So it is environment, health, sustainable mobility, and big data and AI, and capacity building. Okay, so you'll notice the two things you'll notice about this. Okay, one is that these are all linked together. Right, so if you've got sustainable mobility, that will definitely keep the environment cleaner, which will lead to a more healthy life. Right, and then big data and AI are absolutely required to make contributions to all these projects. Right, and then by capacity building, we carry out teaching programs and we teach people about all these things here. Right, so you see that even though they stand out separately, they're all very intricately woven together. Number one. Second point is that you heard Professor Babu Joseph talking about particle physics, and he is the person who has worked on many, many different areas. Okay, but these areas, in some sense, except for AI, to which also he has contributed in the early days, except for that, these appear to be completely complementary. Okay, but the whole idea is that people like us who have worked in our own fields and we have enjoyed doing so, and we have been supported by the government and the people in all our pursuits. Right, so we at some point or the other had to give back to society, and that becomes particularly important in these days of increasing stress because of these pandemics, because of the climate change. You can see the horrific effects of climate change. So it's absolutely essential for each one of us to contribute in a small way to these things. Right, so that is the main thing in starting these clusters. Right, so now we started operations on August the 5th last year. For me, I have had many different projects in my life. I said the project is started when money is in the bank. Okay, no money, no project start. Okay, that's a simple thing. So 5th of August, the money arrived in Ayuka's account. So we started the project that day. But you see, the fact is that COVID arrived in February of that year. So what we did, and this was mainly done by Professor Shashidhara, is that the moment it became clear that we are into an epidemic stage, he quickly got together a number of people working in completely different fields. And then they started collecting COVID data and started different kinds of work. So nearly everything that I'm going to describe today in this domain is entirely because of the start which was made in February and March of 2020, and in which Ayuka was also involved in those early days. Right, so now the nature of these projects is such that all of them are undertaken with institutional and industry partners in and outside Pune. the PKC provides a platform for bringing partners together. And so the more successful we are, the less we will actually be required to directly work on the projects. Because you see, the point is that if we work ourselves, then we can only do so much. But if you bring a lot of people together and they do work on a number of projects, then many more projects will get done. But then the question is, what would be my credibility if I went and told 3 different institutes that why don't you work on COVID? Okay, so the idea there is that we catalyze the process, we start it, we make our own contributions, and we bring together. And in the process, it becomes also essential to bring together different institutions, which normally would find it very difficult even to sign an MOU with each other because of their different natures. Okay, then, as I already mentioned, the projects are scalable to regional and national levels. Now, first, we are all teachers at heart and in practice also. So the capacity building programs are very important for us. And our capacity building program has been going pretty well. And so you see that what we mean by capacity building is try to get people to learn a little bit more about something that they're interested in. And so we have lectures, we have courses, we have internships. We have a STEM program for schools, right? Meaning STEM is science, technology, engineering, and medicine. So for schools, we never thought we would get into that, but because of an accident, when we were talking to one of the funding agencies, then they said that why do you want to only do this for astronomy? Do teach everything. And so one matter which I forgot to mention, very important matter, is that we have been provided funds for our what you call for the core purposes. We have got a grant for the salaries, we have got a grant for the infrastructure, we have got then seed grants for doing a little bit of work, and everything else has to come from outside. Okay, so because otherwise we will become a black hole. Okay, where things come from outside, then it's a white hole. Okay, so that is the point. So now, what kind of these lectures, for example? Okay, so we conduct a number of webinars. Then there are webinar series. For example, the PFC's office and the PKC, or the PKC and Indian Academy of Sciences. So this is India at 75. So Indian Academy of Sciences, they were asked to conduct a large number of activities under this banner, India at 75. So I made them the offer. Then we have a lot of fellows of the academy in Pune. There are about 50 people. So I said that why not have talks by them? And so we do it together, and they're going extremely well. Similarly, there's an organization called CoData, which is the world's premier organization for data. It is called Committee for Data, and CoData has got a national committee. Like all these big things have national committees, and I happen to be the chair of that. So PKC plus CoData and the Indian National Science Academy will together organize these data-related lectures. Now, we have been spreading word about them, but I should tell you that many of these turn out to be extremely interesting. Now, this is a bad time for organizing webinars because there is a serious webinar fatigue, which is there, and then lots of very good people are giving webinars all the time. But the feeling here is that it's a slightly personalized thing, like people that you know are organizing it, and then quite often people that you have heard of will be giving these talks, and there's a chance of interaction and so forth. Then we actually arrange courses. I'll mention that in a moment. Then we have got internships, but internships that will be mainly post-pandemic. We do have a small number of interns now, but you see that the whole idea behind an internship is that the young people have to come and meet the experienced people, and then there have to be a lot of interaction. Now, unfortunately, that interaction now is wholly electronic. I already mentioned STEM and citizen science. I'll come to those later. Then we also carry out senior level programs, meaning that there could be a program on AI for bureaucrats, AI for healthcare, those kind of programs. So what kind of courses that we conduct? So these are typically 10 to 12 lecture courses, and they are on some particular theme. And so far we have been doing it entirely on the theme has been biology and information technology. But what we want to do now is to also take up things like data science, data analytics for the younger people. So I'm soon going to announce a course like that. And then when we are thinking of the first course, we said that what is the course which should interest everybody? So it was in the January of this year. So we requested, and this seems extremely unlikely that they will say yes, but they did say yes. You must all heard about the Serum Institute of India, which is located in Pune. It is only 10, 12 kilometers from where I live, and that is where all the vaccine manufacturing goes on. And so we asked them whether will you give lectures on vaccines. So they agreed. Okay, I asked them in a friend's place, and so they couldn't say no. So the head of the organization agreed to give these lectures. And then, but the one condition was there, and that condition was that no putting out on YouTube, no recording, nothing. Because they said that the subject was so controversial. You may remember all the things which were going on in January, February. They say that anything that they say could be misinterpreted. So they say that they'll be happy to teach, and but that's all. So then we called for applications. That was the first time, and then there were the lectures which went extremely well. After that, we have got these microbial processes. Then there was a course on what is called responsible artificial intelligence. This was conducted by Persistent Systems. So where it is not only AI, but there are certain other factors involved in AI, which are very important from the professional point of view. Then there was an interesting course. It was on natural language processing, but it concentrated on contract analysis, meaning that if one company wants to make a contract with another company, okay, then what are the elements which are involved there, and how can AI help you in that? I mean, this seems unbelievable, but there's a company in Pune which makes $200 million a year doing contract analysis. Okay, so and you may be very pleased to know, some of you who know him, the one person in the world who's like Narad Muni is that you can never predict where you will find him next. Okay, that's a person called Dr. Sunu Engineer. So he came from amongst you in Kerala, and then he joined Ayuka as a graduate student, and he was working in cosmology. I believe he was a student of Padmanabhan, though I've forgotten. And then after that, he took seriously to IT. And wherever you go in the world, uh, it happens that Sunu is there. And then when I was talking to the head of a company called Icertis, which does this NLP, so I tried to introduce myself, and he said that no, I know all about you because I used to come to Ayuka with Sunu Engineer. And it turns out that Sunu Engineer is practically the chief technology officer for the company. Okay, so it's our own people spread all through the world. Right, and then there was this course called Plant Breeding today, and it was actually on molecular plant breeding. And I had never heard of the subject. Okay, but then when we advertised it, 700 people applied in one day. Okay. And it turns out that this is a subject with which everybody is interested, but there is not much of it going on in India, nor in other countries, other developing countries. And so people from all over the world wanted to do it. And then it occurred to me that we should take this up as a major program where we not only conduct lectures, but we also transport people who do well in the lectures to other institutions where they could have hands-on session on this. And the course which concluded most recently was Understanding and Exploring Epidemiology. As you may know, as I did not until very recently, I remember a young relative once told me that she's an epidemiologist, and I asked her, "Does that mean you are a doctor?" That one I did not know what it was. The second great difficulty I had with epidemiology is to spell it correctly. Okay, so it took me a long time because now I need to write and pronounce that word maybe 20 times every day. Okay, so it shows you how you change as you go along. Okay, epidemiology is the thing of diseases, epidemics, and how do epidemics come about? How do they propagate? How do you control them? So it's a very fascinating science. So each one of these courses is a 10-session course, typically 10, 12, 15 sessions, and then coordinated by one or two people. And some of the best people in Pune and in the country give these talks. And so they're going extremely well. And why I'm emphasizing this to you is that we'll be very pleased to conduct courses which will be important for you people in Kerala. Okay, and there is no limitation. And so far, it was like a cosmology of black holes. It is no longer like that. In fact, on biodiversity, which is very, very important for you, and such beautiful work is going on. So we can get together and study all these subjects. Right? Then coming to the completely the other end of the spectrum. And so here we are talking about who are these courses meant for. Those are all for research scholars and young researchers and young professionals. And other thing I should mention is that at least half the lectures and sometimes all the lectures are given by people from the industry. Okay, so the whole idea is to expose industry to young people from young academics, and also to expose young academics to the industry. There is so much which is interesting, which is going on there, and typically we are not aware of it. And just to give you an example of how this might happen, recently, very recently, meaning a few weeks ago, a young person who's one of the few instrument builders in the country. And she approached me saying that she would be looking for a job. She had finished her PhD and a postdoc. So I said I'll introduce her to a couple of people. And I spoke to people from the industry. And it turns out one of the biggest software groups in the country, in the world, in fact, they are quietly starting a space program. Okay, that is because, as you might have heard, our program is also getting privatized, and there'll be a lot of opportunities for industry. In fact, already the industry builds many of the big things that you see, but now it will be much more focused. Okay, and therefore they are picking up people who have experience in that. So if I did not know these industry people, this young person would not have got a job in the industry. So you see that is so it's a very interesting times. All right, now going to the other end of the spectrum. So what can we do for schools? Okay, so we have started a program called SESTEM, which is School Education in STEM. And then there it is in 3 parts, meaning that it is directed toward 3 different audiences. One, the students themselves, from the class 8th to the class 11th. And then their teachers, who also have gaps in their education. And the third group we are going to direct it to some of the better teachers who can themselves be trained to teach this. Okay, so you see that students, teachers, and trainers. And then there'll be 6th, 7th, and 8th. Yeah, I think we started 6th. 8th, 9th, and 10th will be one batch. 11th will be the other batch. And then what we are going to do is to limit it to the Pune district. And then so we'll pick up some schools which are better equipped, and then we will incrementally improve their labs. There's a lot of lab component here, and we'll do this. Now, this kind of a thing needs money. It requires funding. It requires funding because you need several people, experts to be working on it. You need money for the labs and so on. So we are looking for funding. So right now, we'll be most of the money. So where does the money come from? A very important thing which pure scientists have so far missed, okay, is what is called the CSR funding. Okay, there's a corporate social responsibility. So every profit-making company, bigger than a certain size, has to give, I believe it is 0.5% or 1% of their profits for social responsibility. Right, so they are supporting many different programs. But right at the moment, what has happened is that all the focus is on COVID. Not only COVID research and development, but also making hospitals, providing ventilators, providing food to the needy. All sorts of things are going on. And so therefore, some of these programs can be in abeyance, but we are focusing on COVID-related programs. But here too, that there is you see, before I go to that point, just look at it. So big data, capacity building, green coverage, health, electric mobility. So you might wonder what school children are going to do all this. But there is the school children like us. When we were in school, for example, when I appeared for my interview in TIFR, when I went to the advanced interview, I've been asked all the physics questions in my first interview, and I was told that I had answered them all. So the instruction to the senior committee was don't ask him any more physics. Right. So then Professor Yashpal was there. Some of you would have heard about him, and he asked me to name the 9 planets. Right. So then you see that I was finished my MSc, and I was competing to enter into TIFR, and then I wanted to do astronomy. And Yashpal asked me to name the 9 planets. When I named about 5, then he said, "That's enough. You know it all." Right. So now, in second standard, people know all the planets. Okay. So my grandson, who is 5 years old, if I ask him to name the planets, he feels humiliated. He said, "I did that when I was 2 years old." So children now learn much more than we did. And then these topics are there. But the problem is that the teachers are not experienced because the teachers did not learn them. So what we want to do is interesting, is to take all these topics, okay, and then you first of all you align them with a new education policy, number one, and number two, align them with the school syllabus. Because if I tell a teacher that I'll teach you some very beautiful things from quantum mechanics, they'll say tomorrow. Okay, but if what I'm going to say is mapped into their teaching, okay, then they'll say, okay, we'll do it today. So that is the whole point, is that the incentive for them is not only that they learn good science, but the incentive is that it will be useful for them in their own curriculum, for the teachers to teach and for the students to pass exams. And so therefore, this kind of a mapping is required, and which is what we are doing. But while we await funds to carry out this nice program, it occurred to us that the situation is a bit urgent. So these are all the number of programs and so on. The many zeros are here. Okay, but you see what we realized recently was that there's every case for a crash program for teachers in STEM teaching. You see that all the teachers now are teaching online. They can't talk to each other. They don't talk to the students. They're very harassed, and then they're very stressed. And then they need some training in it. Not only training in the online teaching, okay, but also training in gaps. They've got gaps in the knowledge. So what we have done is that we have started a survey, which is being sent to all the teachers in the Pune district. And then the survey has already started. It will be finished in about 8 days from now. And then we'll look at the surveys. We'll prepare training modules. So who will teach? Okay, so you need experienced teachers there. You need people who have interacted with them. So Pune has lots of them, both in schools and in NGOs, and some of us also have a little bit of experience in that. The PKC team, many of them have previously worked at ICER on STEM programs. So what we are doing is that we have got together with Zilla Parishad and with DH, and then we will be carrying out this program entirely in Marathi. And around 3,000 teachers will be trained September to December. So how do we train 3,000 teachers? That is because we'll use Zoom platform, and 1,000 teachers will be attending each lecture. And then there'll be 2 hours of teaching per week, because it has to be consistent with their own other duties, and so on and so forth. And then what we will do is that we are going to upload this on a beautiful site which is run by Infosys. So you'll say that how can somebody in Kottayam benefit from lectures in Marathi? So the people in Kottayam will not benefit from lectures in Marathi. It is the people in Nashik who will benefit from them. Because what we are doing is limited to our own district, but Maharashtra is a big state. But our other programs are all going to be bilingual. Okay, and then there's also the question of translating it. Okay, so if you are such brilliant teachers in Kerala, okay, so and then you see what happens is that if we say that, look, this is what we are doing, you can quickly adopt it to your own circumstances. Okay, so you may need some differences of detail, but the overall skeletal will be the same. So that is what we mean by scalable. So then transfer learning is possible, like you say in AI, and also scalability. All right. Now, big data and AI. I mean, what do we do in big data and AI now? So mainly it's applications. Okay, the applications to COVID data, then mapping and monitoring of tree cover, then in citizen science. And I'll come to these as I go along. Then we conduct courses. As I told you, we've got these 2 courses, and now we want to run a course. It will be, if some of you may know that I used to run these courses with the help of Sajit and others who are present here on carry out everything from Python to statistics, etc., and then astronomical data. So what we want to do is to run similar courses remotely, and then have breakout sessions on astronomy and things on biology. So maybe it will work well. So we'll see. Okay, then we carry out various activities here. For example, a sustainathon has been launched by TCS with our support. Okay, and so at this particular sustainathon is on waste management in Pune. So the idea is that college students and school students will provide are asked to register for the sustainathon, and then they'll provide their ideas as to how certain waste management problems in the city will be addressed, and then then the ones who do the best can actually work them out, and then they get a larger reward and so on. Then there is a roundtable on the 3rd of September. Some of you may be interested in attending it. It's called AI for Good. Okay, so what are the ways in which AI could be applied to everyday problems? For example, in agriculture and horticulture, or on the health side. I mean, how can you do that? So those are the kind of things that we are working on. All right. So now, now I'll come to the COVID-19 project, and you see here that in the first quarter of last year, when the thing went from being a curiosity to it becoming endemic and then to becoming a pandemic. Okay, so we started collecting data. Okay, it is incredibly difficult to collect data because they'll just not give it to you. Okay, but what happened was that we were able to sign in the very early days an agreement with the Pune Municipal Corporation, and so they started giving us the data. I'll tell you what are different kinds of data and what are the elementary conclusions that you can draw from them. Okay, then another thing that we did, and these are all the organizations that are involved in this business. Then we carried out a sero survey. Okay, sero survey meaning you carry out a test to find how many people have developed antibodies, because then you say that those are the people who have been infected. And several sero surveys have been carried out in the country so far, in some places multiple times. Ours was one of the early ones. It was done in the June of last year, and an amazing statistics was obtained that 56% of the people who were tested actually had antibodies. So which means that even as early as that, this has become pretty widespread. Now, there has to be some caution in extrapolating from the results that we got at that time to the whole city, and then to the whole state, and then to the whole country. But already it's said that the prevalence of the disease was far more than what was obvious from the serious cases or even people who had symptoms. So now we have started, we got an idea a long time ago meaning maybe in April also, you see that these variants were coming out. And how do you detect the variants? You have to do genome sequencing. So we said that, look, Pune is a hotbed for this business, so why not carry out 100 or so sequences here and try to see whether we get the variant. Now it turned out that it was easier said than done, and then the project kept growing, and now it has grown into a very large project which involves people from 4 cities. That is Pune, Delhi, Bangalore, and Hyderabad, and Rockefeller Foundation, which is one of the important fund-giving agencies, has given us something like $9 billion, okay, which is to be spent in these 4 cities carrying out genome sequencing. And PKC has been given a very large amount of money to do the data, because we have the best data, and then we have to create the data layers which will be used by all the cities. So this project has already started, and we are very excited about it. But then there is there's also an independent survey which is funded by Hindustan Lever, and which we have to The idea is that you follow people who are vaccinated and see what happens to them over a couple of years period, and also look for vaccine breakthrough infections that you might have heard about, meaning that when both the people, when somebody has got both vaccines, the vaccine one is fully vaccinated, then they still get infected. So why does that happen? And then people get reinfected. Why does that happen? Those kind of very difficult questions. And then we also want to create an epidemiological database. Right. So, let us take a quick look at COVID data, and so you'll see that there are three kinds of data that we have got. One is the daily data. Okay, meaning how many people were admitted, how many people were tested, how many were positive, how many were hospitalized, ventilator, deaths, and so on. So we have got a data for every day since the 12th of April 2020. Then there's the patient data. Okay, meaning that you look at you follow individual patients. Okay, and then you see when they were admitted, where did they come from, can they be relocated, what happened to them, were they hospitalized or were they at home? So this is patient. And here we also need their address, right? And you can imagine how difficult it is in India to have addresses, because they'll say it is behind the Vandana cinema or something like that. Okay. So then you have to know where is Vandana cinema. Right? So now we have got 500,000 data points here. And so it is extremely difficult to analyze the addresses, and we want to do natural language processing to look at the addresses, because geolocating the patient without violating their privacy is incredibly important for understanding and for treating the disease. Okay, then there is clinical data where we actually go to the hospital and get the data on individual patients, meaning that how were they treated, what medicines were they given. You know that different medicines have been popular at different times. Okay, so there'll be a lot of people running behind one particular drug, and then suddenly somebody points in the other direction, they all run behind that one. Now, it is one should not make a joke of this, because when our people who are close to us, when they're hospitalized, when they're very serious, when they're about to die, we are all going to run to get the medicine which is thought to be the best at that time. And so instead of allowing that to continue, the question is, can we study this in detail and find out? So here we have data on 25,000 patients, and then we want to get into another 50,000 patients. And that's one of the projects that we are carrying out. And just for your information, the Pune Municipal Corporation area, so far, this 29 million, that is almost 3 crore tests have been conducted. I'm sorry, 2,900,000 tests have been conducted. There have been 500,000 positive cases and close to 9,000 deaths so far. So then, when we take this very elementary data and then we plot it like this. So you see that what we have got here, and this is an article which Professor Joy Melvin Montero of ICER and I wrote, and we wrote it for the Indian Express. Indian Express, so some of you might be reading it. There's a page called Explained. They explain various things there, and they used to concentrate on COVID during the worst periods of the pandemic. And I found it very useful. And I thought that if I've understood something, let me try to explain it to other people. So that this article came out of that. And then, you see, what has been plotted here is as a function of the date. What you have got is that on the left-hand side, you have got the total number of cases which is detected. Okay, so that is in blue. And on the right-hand side, you have got the positivity. Okay, so what is positivity? It is the number of positive detections divided by the number of patients tested. Okay, and supposing the positivity, you see that positivity here is high, it is at about 0.3. Okay, so what you need to do is to have positivity less than 5%. Okay, because then in some sense, the pandemic is controlled. And you see how you can't make it less than 5%. I mean, but first of all, you have to detect people. So let us suppose that somebody comes there and detected to be positive. What you need to do is to go and catch all the contacts and test them. Right? And the closest contacts will be positive. But then you have to go further and further and further until your positivity rate goes down below 5%. Okay, because otherwise, there are many people who you are not tested who are wandering around the city. Somebody goes to buy vegetables, somebody goes to a birthday party, somebody goes to a wedding, and they're all infected. And so that is this kind of a plot shows you that. Okay, then just for illustration, another plot here. So here you have got something called the number of cases, and on the right hand side, you will see that there's something called CFR, which is case positivity rate. Now there are there are no case fatality rate. Positivity rate is simply the number of positive detections divided by number of tests. Now there's a very intriguing number, which is called the infectivity fatality rate. Okay, meaning that of all the people who are infected, how many die? It is very difficult to get that number. Why? Because a large and overwhelmingly large number of cases are asymptomatic. It took me a fair amount of time to learn the word asymptomatic because I used to call it asymptotic. Okay? Yeah, because I come from a different background. So when you're asymptomatic, again, you're going around the city infecting people. Now it turns out that IFR, that people who have got it, whether detected or undetected, what is it? It depends on your age. It depends on various other factors. But typically, all over the world, it's a small number, like 0.5%, 0.3%, like that. Okay, so now, whereas there's something called the case fatality rate, meaning that out of the detected cases, you may be in quarantine or you may be in hospital, how many people died? Now, that is again difficult to calculate because we see that you admit a certain number of patients today, they are not all going to die by the afternoon. Only a small number will die. And that too, they will die over typically a 15, 18-day period. So the number of deaths in one day has no relation to the number of people admitted that day. So the people who are dying come from different admissions on different dates. So what you require is that you require an algorithm who lets you calculate that from the available data. Again, that's the kind of thing which people like Joy have done. And then you've got the case fatality rate. Now there is something very interesting. Okay, you see that the case fatality rate here is about 2%. Right? But if it starts going up, now you must understand that only a very small fraction of people who have been infected die. But the fraction, the case fatality rate is higher. Now, supposing in one place, a large fraction of people who are admitted dies, that means the case fatality rate is high. What would it mean? It would mean that there's a very large number of undetected cases. Okay, because the IFR has to remain constant at about 5%. So if the 30% of the people that you know are infected die, so it means that there must be 60 times as many infections. Okay, there should be 60 times as many infections. And so these are complicated things. Just look at this diagram. Now, this only describes to you by doing geolocation how the infectivity was, how the number of cases were distributed across the Pune city. But this is my last slide on COVID that I'll show you. So it's very interesting. So you'll see here that this is the test positivity. What fraction of people are testing positive and which is case fatality rate. So you'll find here in these two prabhags are parts of city, which every prabhag has one vote in the municipal corporation, one seat in the municipal corporation, about 100,000 people. So you see that here in these two prabhags, we find case fatality rate is much higher. So which means that there are lots of non-detected cases. So we should show such a diagram to the Pune Municipal Corporation and say, increase the number of testings in this area. So you see that this is pure data analysis. The data gathering is incredibly difficult. The data analysis, the curation of the data is incredibly difficult. Okay, meaning because the same patient will be described in 5 different databases. And so, but once you got that straightened out, then the data analysis is simple. But what such important conclusions can come out of the data? And you and I are all equipped to do this. Now here I quickly want to show you a thing about, you must have heard this business about the total number of COVID-related deaths being far, far higher, okay, than far higher than is actually counted. And there's a very interesting paper. There's a lot of controversy about it by Subramaniam, and who used to be our chief economic advisor, Arvind Subramaniam, and a couple of his colleagues in the US. And 3 days ago, there was a panel discussion with him where he described it. It was absolutely brilliant. But for us, we are used to large numbers. So let me take you through a quick exercise with large numbers. Okay. What is the population of India? It is 1.4 billion. That is 140, 1,400 million. So already I'm getting my zeros wrong. Now you must have heard that that you see that you feel about half the population has been infected through these sero surveys, right? So how many people have been infected? 700 million. So we started 1,400 million. Okay, so how many people are infected? 700 million. Now the case fatality rate I told you is about 0.5%. 1% of 700 million is 7 million. 0.5% is 3.5 million. So even if you say that all these people, 1,300 million people, are not equally exposed, you'll still say there will be at least a couple of billion people, okay, who have died. And the official count is 400,000 people. Okay, so you see that, so there's a very careful analysis has been done there, and it's extremely important to count properly. It is not a question of showing out that somebody is irresponsible, somebody is responsible. It is just a question of finding out about the nature of the epidemic, so that the next time round we are better prepared. The next peak comes, we are better prepared to adjust it. Okay, now so a completely different kind of project, and I'll run through it pretty quickly. I've got about another 10 minutes left, right? So you see that this is a project which is being carried out by Adita Kane and others here, and the project is on trees. Climate resilience, improving the tree cover. So the idea is that trees are a carbon sink. And so the question is, how much carbon sink capacity do we need in 15 years' time? And how many trees to have, how many trees do we need to plant? How much land will be needed? Okay, so the fact is that in Pune, we happen to have data on, I believe, I've forgotten the number, but it is like some 5 million trees. Okay, so actually we know where the trees are, we know what the tree size and so on, what are the tree species. It is not perfect data, but it is there. Okay, so what Anita and her small team are doing is that they're going through the data, they're examining it. And the idea was that now that we're able to go out a little bit, new data can be obtained. But that can be done but some of the calculations can be done in very interesting ways. Is that we have high resolution maps from ISRO of the Pune region. And then those maps can be analyzed, and they are multicolor maps. So which it is like getting B minus V magnitude or V minus R magnitude. So you can get things in different colors, different wavelengths, right? Then it is also mapping the tree cover. But we have data on a very large number of trees individually. So therefore, the idea is that we train a machine learning algorithm to recognize from the ISRO maps details about the trees by using the existing tree data for the training. Okay, so then 2 years down the line or 3 years down the line, if you want to know what has happened, then simply from the ISRO data, you'll be able to get it. So that is a thought. So there are a number of projects like this are being worked on. So for example, here, so you see that DBH, I didn't know what a DBH. Actually, as it turns out, it is the diameter at breast height. So because you need all these parameters for trees and they've been obtained, and then it is being statistically analyzed to see how they will grow if you do water. So very interesting projects. Okay, then a representative analysis of the tree cover. How is it owned, forest land, okay, then private, public, and so forth. So these numbers are there. And one very interesting statistic, which I felt very nice about, is 95% of the trees in Pune are healthy. Okay, that seems unbelievable, but it is very likely to be true. Okay, then we are carrying out citizen science projects in which you motivate a small number of households to reduce their carbon emission by 5%. So this is just various things are being tested. Right, and then other kind of project is afforestation of degraded land. Okay, so there are these large patches of degraded land will be degraded for a couple of 100 years. So you grow a forest there. Okay, then you get all the wealth from it. Then you'll be able to grow things which you could use, for example, in developing biofuel. But these projects are much more difficult to implement than the tree cover project because they require a lot of funding, which is required to carry out deforestation. But there are organizations like that, both national and international, which provide this funding. Okay, so my second last thing here is sustainable mobility. Okay, so one of our senior advisors is a great expert on this, electric cars, electric vehicles. So you have to go there. So you have got sustainable mobility, reduce, reuse, recover, generate and use green energy, city-scale travel demand model, nudging citizens for sustainable transport, etc. And so these are all very major projects. What we have to do is that to break them out into small projects, okay, and then try to do something which is immediately implemented. So one of the things which is happening in Pune right now is that the Maharashtra Metro, Maha Metro, they're setting up a metro system in Pune. Right. So the idea is that you travel in metro from point to point. When you get down, it is like getting down at a railway station, except that it will happen in 50 places in the city. So how do you get down? How do you go home? Some lucky people will be staying within half a kilometer. Other people may want transport. Right. So what kind of transport? Because the metros will be coming again and again. Right. So then auto rickshaws, but auto rickshaws are polluting. So you have e-rickshaws. That's electrical rickshaws. Now, when you want to introduce, or you have small buses which are electrically powered. So the problem is that those buses, they completely clog the inner city areas. So the whole purpose of having the metro is defeated. On the other hand, if you want e-rickshaws, then the petrol rickshaw guys, diesel rickshaw guys, they will oppose it. And so they will say, what about us? So there a very simple solution has been found. You see that e-rickshaws will be light to operate. They'll travel only over small distances. So you offer that you make the spouses and drivers. And so you see that that is the kind of solution which people hit upon because then there'll be no opposition for the rickshawala drivers. Okay, but then there's another problem. How do you charge the rickshaws? So what would be the absolutely ideal distribution of electric charge? So these may appear to be simple problems, but they require very careful analysis. Otherwise, our chaos will only multiply. So you have got EV charging infrastructure, electrical vehicle charging infrastructure, integrated public transport, deployment of green energy, last mile connectivity to the region. So these are the kind of things that we are working on. So you see buses, auto rickshaws, and all these flow charts are there. They're very exciting projects which bring together people from physics, people from biology, people from chemistry, people from electrical engineering. All of them have to come and work together. And people from astronomy are also trying to get their foot in. Right, so now the last part of my thing, which is citizen science astronomy. Now, all of you would have heard about citizen science. Okay, so in citizen science, what happens is that the idea is that citizens contribute to astronomical data monitoring and collection. Now, this is a very big movement. It started as it's called the Zoo Universe, for example, which has built up this fabulous, great atlases of galaxies, and people like us who carry out research at the highest level, so we use the data which has been collected by citizens. So the idea is that can we also do that? So citizens contribute to astronomical data monitoring. We can leverage enormous human resources. The same 1,300 million people that we're talking about in the context of COVID, they also become citizens now. All of them is a citizen. So all of them can contribute to making this data. And what is the use to them? It's developing scientific temper. and familiarity with scientific data, which you absolutely need these days. So what we have done is that we would like to go into big citizen science programs, but we have started because we ourselves have to learn how to develop the infrastructure, which is very difficult. It requires a lot of work. And so we have started with amateur astronomers and experienced science enthusiasts. And we have set up the program. Okay, the main problems are IIA Bangalore is now helping us very much, but there are different kinds of criteria. ICOM will come into the picture also. Okay, and so what is the approach which is required is that you develop a website because you interact with the public through the website. Identify projects, register participants, provide training, initiate the project, curate the inputs. You have to see whether the inputs are reasonable or not, create a database, and hopefully, sometime in the distant future, publish the results. But the database can be used by many, many people. So what are the kind of projects? So I went to very reliable people to identify projects. One is, of course, our long-time collaborator, Sudhanshu Barve. And other one is other long-time collaborator, Vivek, F. Vivek. So then he, so whatever small number statistics that you see here is actually quite true. In any large astronomy project, okay, about half the persons now are from Kerala. Right, so so you must it's something which just didn't exist 30 years ago, but which has become increasingly true now. So out of these two projects, one is from Kerala. So you see that here, one is galaxy classification. Now the Zoo Universe projects ask you whether a galaxy is a elliptical galaxy or a spiral galaxy. So what we thought to do was to go deeper into that, meaning that this galaxy has got a ring around it. These galaxies are interacting. Okay, you can clearly see the interaction here. So can we get people who are not trained as astronomers to detect features like this? And what Vivek has suggested is that you look at the spectra from the Sloan. I mean, he's a great expert on the use of Sloan. And then you look at the spectra and you compare them to see if there is variability, for example. Very simple projects. Okay, so morphological features in galaxies. So all of you are familiar with these galaxies, with this beautiful galaxy. We are used to a spiral galaxy like this, and then there's spiral arcs, there's a bulge, there's a disk. But then you see, if you come here, you'll see that each of these galaxies has got this linear structure, which is a bar. About half the galaxies are bars. And the question is, can we find them? As it turns out, this problem is simple enough that it can be addressed by an artificial intelligence system. Okay, and and I worked with Shilu, who's, I believe, attending this talk, and then she was a postdoc in Ayuka at the time. Okay, and Shilu and who else was the person who was working even now. I'll tell you the name in a moment. So then we did this problem, and we set up a deep learning method actually for Arun Anian. Arun Anian is the person here. So he wrote the code, he did the training. And so what we are doing here is we have got a beautiful deep learning system, and then they for detecting bars. Okay, but now when there are more complex structures, okay, so you can see you see that there are a lot of very complex structures here. For example, there are things like pseudo bulges which are there, which are to be distinguished from bulges. Okay, or else you can see here rings. These galaxies are outer rings. Okay, some galaxies have inner rings inside. Okay, then here there's an outer pseudo ring. Now, as it happens, we could train an AI-based system to recognize these features, right? But we simply don't have large enough training samples for that at the present time. So what we need to do is to train humans to do it. And that is how our project is doing. And what we have done is that we have developed this website, and you can come and you can participate, you can register yourself, right? And then you're finding features in galaxy images. And then you are trained. I gave a couple of lectures, and then Disha Sawant, Dr. Disha Sawant is a person from our side who's leading it, and Sudhanshu and she carried out much more detailed training. Okay, and then you see the whole idea is that so the person, a participant looks at a thing like this and says, are these interacting galaxies? Are they tidal tails? Is this a group of galaxies? Are these galaxies edge on? Is there a dust lane? Are they smooth and no features at all? Or are there features that you can see but which are not the ones which are listed here? All that the person needs to do to take a careful look at the image and tick these boxes and submit it. So you see how simple the participation is. And people are actually enjoying doing this. And then since most of the people are inexperienced, how do we know that they're doing it correctly? For now, our own training is going on here. So what we have done is that all the 100 participants, 200 participants have been given the same data. And then we'll compare it. And then we'll see what people can do or what they can't do. But once the project starts going properly, okay, what happens is that we will take 5 people, 8 people are given the same data. And then we compare that and then we see what the probability of the thing being genuine and so on. And so these are the statistics that we have collected. A couple of 100 people registered and then 100 people participated in it seriously. And we actually have got a database of 15,000 classifications already. And this is in about 20 days time. Right? And then what is the thing here? Students are here and then working professionals, all kinds of academic types and doctors. And we did invite them. But you see, because they're the magic of social media, they got hold of it somewhere or the other and they participated. And homemakers are there, okay, and others, including senior citizens, amongst which I count myself, but I did not actually participate in this. Right? So what happens is that all the different people are doing it, and it collected 15,000. So now we are going to advertise this. We are going to give it some publicity, and the slogan is going to be 1 million more. Because I asked Sudhanshu day before yesterday, how many would you need to make a decent sample? He said 1 million. Right? So if 100 participants in 2 weeks or so can do 15,000, 1 million is not such a big number. It's only 60 times this. Well, my feeling is that if we all work hard and if you persuade your students to participate, okay, then we'll do that in 3 months. And then just can you imagine that when we say that we are going to 1 million, think that 3 million, 5 million is no problem. Then the project will start rolling forward autonomously. Right? So not only am I trying to persuade you to bring your students to these projects, number one. Number two, if you have any projects in mind, we can run those. Okay, so for example, if Ravi wants to run a project or Shilu wants to run a project, you give us the idea. You see, this requires quite a lot of infrastructure. Okay, so there'll be, say, 5,000 people logging into your site and doing it. Secondly, you have to reach out to them, you have to train them, you have to answer their questions. Typically, even very talented people like all of you would find it difficult to devote time enough to develop the infrastructure. But fortunately, because this need has been recognized, we have the infrastructure. Not all the infrastructure which is needed, but we have something which can start us off. Right? So therefore, I'm appealing to you. In this specific case of taking it to 1 million, you become our partners. Okay, I'll stop with that. Thank you very much. Here's one thing which we're also starting, astronomy for the visually impaired. That has been done by the IAU, and we are also starting that. We'll get hold of a 3D printer, okay, and then you produce these models, which the people, visually impaired people can look at and get some feeling for astronomy. And there's something called sonification, which is also being done, where people will hear the images rather than see them. Thank you.
Thank you, Ajit, for this interesting, really fascinating new project on the Pune Knowledge Center, Knowledge Cluster. There are, I think we can have a few questions. Meanwhile, in the chat box, there are a couple of questions. Should I read, Ajit?
Yes, please. That'll help me.
Yeah. Is it true that children from rural areas in India are highly indigenous and eager to learn science subjects?
You see, I'll tell you what. I have had a fairly long career in the science and in astronomy. Okay, and I have worked in good places. I have traveled all over the world, met people, and 98%, 99% of the people come from an ordinary background. They come from small towns and villages. Okay, and they come and become big scientists. Okay, so it is just spread through the population. Okay, it is not at all the domain of just a privileged few. Then in a case like Kerala, tell me what is a village and what is a city.
Yeah.
Right? And fortunately, you people are very fortunate, but the other parts of the country also, which are not so well developed, they are also getting into that. I told you that we are teaching these 3,000 school teachers. In every session, 1,000 of them will be logging in. Okay, and they're distributed all through Pune district. Right. So even when we have these grand meetings, day before yesterday we had a meeting of the advisory committee here, and one person who is a truly well, who's not in the billionaire class but getting there, he said that so my internet connection went off, so I couldn't attend. So we are all in the same boat.
Yeah.
And the further you go from the city areas, okay, the better are the people that you find.
Okay. Another question from the same person, from K. Rajagopal.
Hello.
Yeah.
Hello, Ravi. Dr. Ravi, I have a question.
Yeah, please ask, Sajid.
Sir, I am Dr. Saji Agustin. I have one question.
Yes, please.
Can this capacity building courses, which you have city alone or for entire India, can it be extended to Kerala community as well?
Yeah, you see, what happens is that all our courses, except one, I mean, when we asked the Serum Institute, they said no, but everybody else has agreed to live streaming, and then they are on the YouTube. You can always watch them there. But you see, there's a problem with that. On YouTube, you'll get the most magnificent material. You can find all of Stephen Weinberg's courses on YouTube. Right? So that becomes a second order effect. What you require is something which is designed for you. Right? So we'll be very happy to conduct a course for you. So you say what you want the course in. Okay, then we'll take some teachers from your side, some teachers from our side. We'll design the course, and then people will find it. And when they give the talks will be live on Zoom, and then people can ask questions just like you are asking questions. And then there'll also be the chance of a follow-up. Right. So my brief answer is that everything that we do is publicly available on YouTube and Zoom, and it will also be on the Infosys platform. Right? But we'll be very happy to specifically design courses and give them for you in care. And at that time, of course, everybody from Kashmir to Kanyakumari can attend them. Okay? But the focus will be on something which you are interested in.
What about the industrial collaboration like internships for degree students?
Yes. At the present time, as I said, we are not doing internships, but our internships also will be open. But you will find it best to do all this if you gather together and say that, can you have a cluster? Okay, then the way I would do it is I'll contact people in PS's office. They say people are saying, for them, people are saying is very important. Okay, people are saying that there's no cluster in the south. And so then you say that fine, we will put a cluster in Kerala. But for that, you require some local support. You will need to gather together people from academics, which you are all there, and industry.
Sir,
Right.
there's the basic problem is there is no connectivity between the industry and the institutions.
So
particularly,
what we'll be very happy to do is to motivate you to do that and also make it possible for you to do that.
right. Thank you.
Okay? Because I'll be very happy to do that.
I will
But
contact you personally.
for that, you have to invite me to Kerala, nothing on webinar, nothing on Zoom.
Okay. Thank you, sir. Thank you. Bye-bye.
Yeah. Can I ask one question, Ravi?
Yeah, please.
Yeah. So, Kumbhavi, I'm Suresh from University of Hyderabad. So, you want to know about the more Galaxy morphology projects you are talking about.
Yes.
See, suppose students want to do some summer project or a part of their MSc curriculum project. If you use that one, is it a legally problem? Use the data, write the part of their project report.
The data is specifically to be used. Okay. All the data that we produce, we're completely in the public domain.
Okay.
Okay. And half the astronomers sitting here use public data. So there's absolutely no problem.
Okay.
So what we will do is that, I mean, how many projects are I giving? But we are developing these platforms for projects also, because I keep getting every day some 3 things requests from a young person to do a project. Okay, so the thing is that many of you sitting in relatively distant places will be very happy to have good project students. Right? So we can connect you together.
Yeah, because there are a large number of students are interested to do this kind of small projects. I think they
Exactly.
can participate.
Right? And so one can have this thing where projects are defined, but for that, teachers like you have to take interest and spend some time. But if you are willing to do that, then this can be done very well.
Thank you.
Yeah. Is there any more questions? I
All right.
ask one question. It's on this our COVID data from the CFR, and it was in the beginning the CFR was showing pretty high.
Yes.
And later it settled down to that 0.5 or 1% low.
Yes.
So were there any analysis going in saying that, I mean, what
No,
kind
that's very simple to understand. You see, what happens is that in the beginning, when people are not aware of the disease, and moreover, you don't have the thing, they don't even know that they have got it. Okay, so that is why all those who are admitted are very serious people. They start gasping for breath and they come there. And in the hospital, there is no ventilator.
Okay. Yeah.
Right? So people die. So at high CFR, as I showed you, what it means is that there are a lot of undetected cases.
Yeah.
Because you are not doing enough testing.
Yeah.
As testing ramps up. Okay, at the present time, the testing in Pune is like 8,000, 9,000 per day. Okay, and then the thing is the positivity is about 3%. Yesterday it was little over 3%. Okay, but the worrying thing is that 8 days ago it was 1.5%.
Okay.
And the graph that I showed you, so first the positivity starts increasing and then the numbers start increasing.
Yeah.
That is the problem.
In Kerala also it is actually the other side now, because it
Yes.
is.
So for example, if you people can also gather the data and study it like this, it will be extremely useful. What you should do is that you should talk to the lady who was the health minister.
Yeah.
The past, right? And she can give you access to the data. If the current one also can give it, but the other one will have more time.
Yeah.
Right? And you can get this data and then you can just adopt all the things that we have been doing here very quickly and analyze.
I think they are parallelly doing that.
Yeah, the people are doing it. The point is that people like you need to do it.
Yeah.
Because you have, in some sense, and this is not a politically correct statement, in some sense you have better understanding. Because you had worked on data for not 30 years, 20 years. Okay, then, thank you very much for listening to me patiently. And I can only, I'll end my thing here by saying just one thing. I would have been extremely and genuinely happy if Professor Kuriakose were attending my talk today. Because you would have smiled very benevolently and you would have sent 2 students to me to work on it. Okay.
Yeah.
Thank you.
Thank you, Ajay. Thank you. It was really interesting to hear you and happy to see you again.
Yeah.
Lilava teacher, yeah. Teacher, mic mute irithunde.
Yeah.
Let her.
Thank you very much.
Yeah. Thank you.
Maybe there are a couple of questions in the chat box, I suppose.
I'm sorry. There are. Let me read that also then, please.
Yeah, quickly. I'll of course be attending the next talk, but I need to do something. Please tell me.
COVID-19, while handling the data on casualties, is it possible to know how vulnerable are the patients with comorbidities?
Yes, absolutely. So you see, what we are going to do now, in order to do that, you need to create a database. Okay. Secondly, these are not linear relationships. These are all essentially highly non-linear relationships involving a very large number of parameters. Okay. And therefore, a machine learning approach and a deep learning approach is going to be very important. Okay. And then you see that we have got tens of patients, data on tens of thousands of patients. But we don't even have a handful of people working on them. So that is a problem.
Okay. In data handling of COVID pandemic, cumbersome as you described, is quantum computation of any use?
You see, quantum computation is simply a computational method, right? So therefore, all computational methods will be useful. But if I wait for quantum computation, by then there will be some fourth pandemic after this. Okay. So what we are doing is that we are taking a much more practical approach. We are buying a compute server, and we are putting 2 state-of-the-art GPU cards in it. Okay, and that will be completely enough to carry out all the analysis. All that we require is willing, clever people to be able to do the analysis.
Yeah. Finally, it is a matter of pride to know the scientific community of our nation is putting in great deal of efforts in areas like handling of COVID pandemic too. Hearteningly, the legacy of Vikram Sarabhai by developing indigenous antennae for handling communication satellites for education. Sorry, sir.
Yeah, it's a very important thing. If we did not have this kind of communication channels,
Maybe that is not a question. I think that's a comment. There is
Yeah,
another
yeah,
question next to that.
Yeah, but still, it is important to realize that if we did not have this communication channels, I would not be giving this talk today.
Yeah.
I think scientists better be interested in it, because if they are not interested, then they'll all be dead and gone like everybody else.
Yes. As a budding, Archit Ashwati is asking, as a budding architect and urban planner, are there any opportunities to work at or contribute to IUCA in the fields of urban tree cover and sustainable mobility?
Oh, absolutely, absolutely. Okay, so because you see that we are all in it together, right? Okay, so the urban planners, so they will tell us where the trees should go. So you plant a tree in the middle of the road, is not going to work out. You plant a tree in a place where there's going to be a road in 5 years' time, it's not going to work out. Just when the tree is growing, they'll cut it down. So urban planning is integral to all this. Okay, in fact, I gave recently a talk to a college of architecture for these things. Okay, now I must really go, but I'll be very happy to engage further with you people on it.
Thank you. Yeah. Thank you.
Okay, thank you, Ravi. And as majority of you may be knowing, Professor Kembave has played a very significant role in the development of astronomy as a research area in Kerala. And he was very close to Kuryakos sir. On behalf of VCK students, let me sincerely thank Professor Kembave for his presence and the enlightening tone. Thank you, Ajit. Thank you so much.
Thank you. Bye. I'll be around. I'll listen to the next talk.
Okay. Next, we'll have the second session by Dr. Chaji N. Let me invite Dr. Taranath R. from Aquinas College to take charge of the session.
Okay, thank you. Am I audible?
Yes, Taranath.
Okay, so welcome to the last session of this program. And the title is The First 3 Minutes and Beyond by Shaji sir. And from the very title, it's pointing that about Stephen Weinberg and all. Kuryakos sir, while we are doing PhD time, he was very fond of Weinberg, and he insisted us to read his books and all, and we bought that book as well. And at the time of his, demisal of this Weinberg, we thought of having a lecture regarding his contributions to physics. And under the discussion, it's came to the conclusion that Shaji sir is a very apt person to have a lecture on this, because he has done a lot of popular lectures on physics in the layman language. And I will introduce Shaji sir to you. He has done his MSc from Cochin University itself. Then he did his PhD from Indian Institute of Mathematical Sciences at Chennai, which is a very premier institute in India to do theoretical physics in quantum field theory. Then he joined in a government college in Kerala and worked in various government colleges in Kerala, and mainly in Maharajas College, Ernakulam. He retired as a principal in the Manimala Kunna Government College. And presently, he's again back to Cochin University and working as an adjunct professor in Department of Physics. More than that, he's an editor of the Luke Science Journal, a part of Sahitya Parishat, Kerala. He's a very reliable person in Kerala to, a lot of discussions in physics. And I think in all the physics groups in Kerala, WhatsApp groups, he's the most the reliable person to answer coming with the authentic answers in physics in a very simple manner to each and every one of you. So I hope this session will be very fruitful to mainly to students. We can have a general idea about Weinberg as well as his contributions, and as the title says, the first 3 minutes and beyond. So I welcome Shaji sir to deliver the talk. Sir, please.
Thank you, Taranath. Extremely grateful to Taranath and friends for inviting me to this talk. I knew Professor Kyriakos from my student days. The time when I was a student in Kusach, he was still in UC College, but he was working in quantum field theory, finite temperature field theory. And incidentally, I did my MSc project that Professor Babu Joseph in finite temperature field theory. And it so happened that Professor Kyriakos was the examiner for the MSc projects. And we had a good interaction. And even later, when I was working in Maharajas College, I used to contact him in activities related to amateur astronomy, etc. And I know I'm a teacher also, and most of his students are known to me. And I know that many of you are well versed in the topic that I'm going to talk about, but I'll assume that I am addressing students from BSc and MSc classes and give a lecture at a very popular level. I hope that students of BSc also will be able to understand it. So let me start by sharing my screen. I think you should give me permission to start screen sharing. It says host disabled participant screen sharing. Taranath, please let
one moment, sir. One moment.
But you are the co-host.
Okay, thank you. I hope you can see a screen.
Yes.
Okay. I think many of you know about this book by Steven Weinberg, The First 3 Minutes. It actually talks about the first 3 minutes of the universe. So when you say universe, it means everything that you see around the Earth, the planets, solar system, then galaxies, cluster of galaxies, etc. And Weinberg's work was mostly in particle physics. But interestingly, there's a big connection. That when you go to the highest, largest scales, you talk about cosmology and the origin of the universe. It's deeply related to the smallest of small things. And Weinberg tells the story in a very interesting manner in the book First 3 Minutes. This is one of the best popular science books that I have read. And for students, I recommend it because it gives a lot of insights into how physics works, its history, and how the questions change, how the answers change, and this will be a good exercise on the method of science also. So I'll be generally talking about basic principles of cosmology and some interesting facts. Galileo Galilei is one of my favorite scientists, so I will start with the painting of Galileo showing his telescope to some important people in the Catholic Church. And actually, Galileo was very much interested in popularizing science and its method also. Those days, usually people used to write in Greek or Latin, but Galileo wrote his books in Italian. And within a few months of his using a telescope, he wrote a very nice book called The Starry Messenger. That's the English translation, and students can download it. It's a Starry Messenger, and that name is book is very interesting, and you'll get a lot of ideas. Just let me write down the name. Starry Messenger. See, I want to tell this because it was the invention of a telescope that sort of revolutionized the study of astronomy. Our idea of the size of the universe underwent a drastic change after the discovery of a telescope. These are some of the drawings from Galileo's book, Starry Messenger. Left side, you can see part of Orion constellation. And these small stars there he has marked. These cannot be seen with naked eyes, but you can see with telescopes. So Galileo was astonished that there are very large number of stars which are not seen by naked eyes. That is an eye opener in the real sense. And telescopes were eye openers that could open a large window to the universe. You can see a large number of stars which cannot be seen with the eyes. And on the right side, you can see his drawings of Jupiter and its moons. The early days, he saw only 3 moons because either 2 moons were very close or close to each other or very close to Jupiter. But then within a few days, he realized that these are moons going around Jupiter, satellites going around Jupiter. And that meant that the belief that Earth is the center of everything, of the emotions of the universe, is not right. And at least he could argue that, say, Jupiter is also a center for its satellites. So this was another interesting thing. And the idea of universe changed with these observations with the telescopes. And Galileo could easily establish that sun is the center of the solar system. When he observed Venus, it showed the phases. And the only way to explain that was to assume that Venus is going around sun. So with Galileo's observations, it was established that sun is the center of the solar system. At that time, probably it was thought that it's the universe itself. And of course, Copernicus had proposed this idea earlier. but people had not accepted it. Even when Galileo proposed this idea, there was a lot of opposition, both from the church and also from many fellow scientists. But within few years, this all evaporated. This is also Galileo's drawings of moon. Earlier, the belief was that celestial bodies are perfect objects, but Galileo showed with his telescope that moon, you can see these craters and mountains. That means they are not perfectly spherical objects. And the case of Saturn, he could see the rings, but he could not make it out that it's actually rings because his telescope was not good enough. And on Sun also, he's found these sunspots. It also shattered the idea that all these bodies are heavenly perfect bodies. And this gave a idea that you can extend your theories developed on Earth to celestial bodies. People were convinced that these are all these planets are like Earth, and our ideas of physics could be applied to these things. These are the people who are shown are Tycho Brahe and Johannes Kepler. Tycho Brahe was a great observer. He lived in the age before a telescope, but those days he had the best observatory. See, those days, in 16th, 17th centuries, Europeans were involved in navigations across oceans, and astronomy was a very useful tool. And there was a good funding for astronomy, and there was a lot of interest in astronomy. And Tycho Brahe made use of this to employ several people to make observations. He had the best observations, and he had taken observations over several decades. And these were passed over to Johannes Kepler, who took several years in data analysis. He went through this data of Tycho Brahe, which was very good, which has a good accuracy. He had achieved the accuracy that is achievable with naked eyes of the order of angular resolution of the order of minutes. And this was very useful for Kepler to show that planets actually move in elliptical orbits and not in circles. Let me remind you that only with very good observations you can make out the difference, because though you say that it's all an ellipse, it's hardly distinguishable from circle if you don't have good data. This is Isaac Newton. And what is showed is a Greek text. In the early years, Einstein used to write in Greek and Latin, then switched to English when he wrote optics. Like Galileo, Newton also did a lot of experiments. He also devised the telescopes. Most of the amateur telescopes that we use these days are known as the Newtonian telescopes. And using the observations of people like Galileo, Kepler, he could develop further with his theory of gravity. And this was very useful in analyzing cosmological questions. With a simple theory of gravity, he could explain lots of things, like how these planets go around the sun in elliptical orbits, how do satellites go around planets, and how tides occur. He could also predict the movement of comets and things like that. And he also could do some calculations of cosmological significance. For example, there was a question: if Earth is attracted by sun and it's going elliptical orbit, what will be the effect of distant stars on the movement of Earth? And to calculate that, he had to do several detailed calculations. For example, Newton argued that these stars, distant stars, are like our sun, and they appear to be so dim because they are very, very far away from us. And he could even calculate the distance. He assumed that many of the bright stars are as bright as, say, Saturn. And assuming that he could calculate the distance to these stars. How did he do that? He assumed that it's the sun's ray that is getting reflected from Saturn that shows Saturn with so much brightness. And you can make a theoretical calculation. How much of sunlight will be reflected by Saturn, because people knew about the angular size of Saturn and approximate distance. And if a star appears just as bright as Saturn, what will be the distance? And he could show that it is typically of the order of 1 million times larger than the distance to Sun. Assuming that these stars have a mass comparable to Sun, but the distance is 1 million times larger, you can infer that the gravitational force of these stars will be 1 million times smaller than those of that of this Sun. So in that way, he could account for the movement of solar system planets, and he could also make an estimate of the distance to stars, and that was kind of mind-boggling. Earlier, people did not have any good idea of the distance to these stars. People only knew that they are at a large distance. So our scale of the universe became larger. And there was another question. If the stars are distributed uniformly, then they will have an attraction between them. And there's a chance that the stars will come together and coalesce. So what was the argument against that? So Newton came up with an argument that if the universe is infinite, force of one star will get cancelled by other stars on the other side. For example, if you have 3 stars in a line, the star at the center will have force from both the stars on the left and the right, and they will cancel. So this happens only if you assume that the universe is infinite. So Newton assumed that from this argument, Newton sort of argued that the universe is infinite. But he assumed that the universe is static also, because there was no evidence at that time to say that the universe is actually expanding. Let me go to next slide. Then came after about around 300 years, then came Albert Einstein. Then he revolutionized the physics with his theories of relativity. And he was fascinated by observations of Galileo and Newton that gravitational mass and inertial mass are one and the same. He thought deeply about it. And he was also fascinated by Maxwell's equations, which says that speed of light should be independent of the inertial frames of reference, and made that into a postulate, and he developed the special theory of relativity and later general theory of relativity. And that is the foundation for present day cosmological theories. Just after Einstein wrote his equations of general relativity, many people tried to solve his equations under various conditions. People like Schwarzschild. Then this is actually Lemaitre. And Lemaitre got a solution which showed that universe actually expands. And he could even make an estimate of what is now known as Hubble's constant. It should be actually called the Lemaitre constant. But nowadays, many people call it Lemaitre-Hubble's constant. So he showed that Einstein's theory implies a non-static universe. But I don't know whether even Einstein took it seriously. Einstein himself solved his equation, and he was perplexed to see that a static universe is not possible. But for some historical or philosophical reasons, Einstein believed in a static universe, and he sort of modified his own equations to accommodate a static universe by introducing what is called the cosmological constants. Then Einstein is supposed to have said later that that was one of his biggest blunders, the idea of introducing cosmological constant to keep the universe static, because a few years later, Edwin Hubble, with his the then best telescope in the world, the telescope Mount Wilson, and he could observe distant galaxies, and that showed what is called the redshift. Let me just explain for students what is meant by this redshift. See, if you look at the spectrum of stars, you will see certain absorption lights. See, sun, for example, gives light in all colors from violet to red. But if you take a good spectrograph of sun's spectrum, then you will see dark lines, which are called Fraunhofer lines. And some of these lines are very special. For example, there are something called the K and H lines of ionized calcium. K and H lines of ionized calcium. These are lines with some separation, and these wavelengths are known. So if you look at the spectrum of a distant star or a galaxy, you'll be able to identify these calcium lines, K and H lines. But some of these lines appear to get shifted to the red side, because these are actually seen in laboratory. These are seen in the violet region, but for some stars these get shifted to the red region. That's called the redshift. And the simplest expression for that is the star or the galaxy is moving away from the observer, and from the amount of redshift you can make a calculation of its velocity. And for several galaxies, you will get speeds of the order of hundreds of kilometers per second. And by careful analysis of the spectrum of galaxies, people like Hubble, with the assistance of people like Hubble, he could even estimate the distance to these galaxies, because you look at some brightest stars and estimates its brightness. From that you can make an estimate of the distance. And Michelson's time, the estimates were not very accurate, but he could draw some graph like this. On the x-axis, distance is shown in parsecs, and on the y-axis, you can the velocities are plotted. The velocity estimates is reasonably accurate, but the distance estimates are not that accurate. And if you look at this data, it's not very clear that it shows a linear behavior. But Hubble actually drew this graph of a linear relation between velocity and distance. Some people say that probably he already knew about Lemaitre's work, which had predicted a linear relation between velocity and distance. And he asserted that this is true. This was in 1929. Once this was announced, people like Albert Einstein said that his assumption of static universe is wrong. But then data came pouring it. With more data, within a few years, it was established that the distant galaxies are moving away from us. If you look at galaxies like Andromeda, this actually shows a blue shift. But if you take distant stars, they all seem to go away from our own galaxy. And this was the important result that Hubble got. It was verified with more and more data later. But at that time, there was a limit to the power of telescopes. Then Second World War came in. There was not much communication between scientists, and there were no attempt to make big telescopes. But after Second World War, new telescopes were built, and there was more communication between scientists. And this was established that the universe is actually expanding. This is what I mean by expanding universe. When distant galaxies are moving away from ours, and if you have this linear relation between velocity and distance, you can infer that you can take any galaxy as the center, and from that you see the distant other galaxies are moving away from it. So our galaxy doesn't have any special role. And another important thing that people like Hubble realized that see, galaxies like Andromeda are quite far away from us. The present estimate is that it's 2.5 million light years away from ours. So that's a big scale. During Newton's time, it was realized that stars are at a distance of light years, though that was not the unit that was used then. But from light years, now you are going to millions of light years. So many galaxies are even nearby galaxies are at a distance of 20, 30, 40 lakh light years. So our idea of the size of the universe increased manifold with Hubble's observation. But still there were some problems. For example, Hubble first estimated the Hubble's constant to be around 500 km/h per megaparsec. That is, if a galaxy is at a distance of 1 megaparsec, it shows a redshift of corresponding to 500 km/s. With that estimate of Hubble's constant, if you make an estimate of the age of the universe, that will turn out to be around 2 billion light years. Actually, there is some disturbance coming, audio. If everybody can mute, okay, it's okay now. Okay. So with the estimate of 2 billion years, 2 billion years for the age of the universe, there was a big problem, because people like Rutherford had estimated the age of Earth, and it was definitely known that it is more than say 4 billion years. So the interesting thing came, and result came that the age of the universe is smaller than or lesser than the age of Earth or solar system, and that is absurd. So many people did not take this Hubble's idea of expanding universe seriously, and alternate theories also were developed, like steady state universe theory. But then with the new telescopes and the identification of Cepheid variables, distance to galaxies could be estimated with much more accuracy. and that Hubble's constant value was updated drastically. Later, it was estimated it's between 50 and 100 kilometers per second per megaparsec. With that estimate, the size of the universe actually increased manifold. And with the new telescopes and good photographic techniques, more and more galaxies could be seen and the distance to them measured. And it was established that the Hubble's law is valid. So then this question came: if the universe is expanding and galaxies are going far away from each other every day, then if you go to in the past, the galaxies should have been closer together. So if you go back in time, there should have been a time when all these galaxies were together in a very high dense state with a very high temperature. And this idea was picked up by people like Gamow and his student or assistant Alpha, and they worked out some theories. If the origin, if at the beginning the temperature and densities are very high, there's a possibility that mass will be created from energy. For example, if you have a lot of energy, electron-positron pairs can be created, proton, antiproton pairs can be created, neutron, anti-neutron, all this could be created. At that time, there was no idea of quarks, so they talked in terms of protons, neutrons, electrons, and their antiparticles. So they made an estimate that a large amount of these fundamental particles could be created, and they made an estimate of how these protons and neutrons could come together to produce other elements. So they wrote a paper on with the title "The Origin of Chemical Elements." The list of authors is very interesting. It says Alpha, Bethe, and Gamow. And that rhymes with alpha, beta, and gamma. Actually, Bethe was not involved in this work. Gamow just added his name so that this could become alpha, beta, gamma paper. Actually, Alpha was not happy with the adding Bethe's name, but anyway, Gamow was an interesting person. He just added Bethe's name. Actually, Bethe has done a lot of other work related to production of energy and nucleosynthesis in stars. But in this particular paper, he did not have any contribution, though his name is there just to rhyme. So this alpha, beta, gamma paper put forward this theory that in the early universe, the temperature and density is very high, and universe started from that state, and from that the elements could be created. For example, they showed that with the proton and neutron, you can create isotopes of hydrogen like protium, deuterium, and tritium. Then helium-3, helium-4. But then they realized that the other elements cannot be produced with that kind of abundance. And at that time, anyway, they could not do a very accurate calculation because of two reasons. One was that nuclear physics was not that developed at that time. And also because nuclear physics was connected to the making of atom bombs, much of this information was held confidential. But later, with detailed data available, people could make out that what could be produced in the early universe was only hydrogen, its isotopes, helium and its isotopes, and a little bit of lithium, small amounts of lithium, and the heavy elements could not be produced in the early universe. But this was an interesting observation. And later, people like Cecilia Payne, right? She made a lot of observations of different stars, and actually showed that this is right, that most of the stars, and in fact the whole universe, if you make the estimates of different elements, hydrogen makes out comes to be around 75% and helium around 24%. And this is the prediction of people like Alfred and Gamow. And it turns out that even the other isotopes, they come in the right proportion. So there are, if you make this calculation, there's not much freedom in doing the calculation. There's only one parameter that you can actually change. That's the ratio of photons to baryons. So once that is fixed, that relative abundance of light elements are fixed, and that turns out to be very accurate. So this data gives the relative abundance of helium-4, helium-3, lithium, deuterium, etc. And that's in a good agreement with the Big Bang hypothesis, which says that in the early universe, the densities and temperature was very high. Another prediction of these people was that if the temperature is very high, there should have been a background, there should be some black body radiation, because any body at a temperature will emit radiation. In the early universe, it was quite opaque, so radiation could not come out. As the universe cooled to temperature around 3000 Kelvin, protons and electrons could combine to hydrogen, and alpha particles and electron could combine to form helium, and hydrogen and helium are transparent, and then radiation can expand. Radiation can freely move, and as the universe expands, the temperature will come down. There will be a cooling down, and they predicted that this should now appear as a microwave. And these two scientists, Penzias and Wilson, they were using this big horn antenna, and they realized that there is some radiation that is coming from outside the solar system. And with very good reasoning and very accurate measurements, they could show that this is some microwave coming from outside the solar system. And then later they were told that this is already a prediction. Scientists have predicted the existence of such microwave radiation, and it turned out to be what they have observed was just the microwave radiation predicted by Big Bang hypothesis. That gave a big boost to the what is now known as a Big Bang theory. So this is a strong evidence for the hot initial phase of the universe. And this is data from COBE, Cosmic Background Explorer. And that blue line is the theoretical curve for a black body radiation, and the red marks show the experiment observational values. Actually, this microwave background radiation is both in microwave region and infrared region. Our Earth's atmosphere is not transparent to this infrared. So to make good measurement, you have to use satellites. So COBE could bring in a lot of interesting data. And there's a perfect agreement between experiment and theory. That is between the theoretical curve of black body radiation and observed values. So this is a great achievement. And the deviation from the theoretical values are very, very small, of the order of 1 in 10,000 or so. And even that small variation also becomes important for some other studies. And these are the people who involved in the COBE experiments. Mather and Smoot, both of them got Nobel Prize. Earlier I had mentioned Penzias and Wilson. They also got Nobel Prize for detection of background radiation. And this is another experiment using WMAP, Wilkinson microwave anisotropy probe. I said that there's a small difference in temperature. If you look at different regions, temperature variation of less than 1 part in 10,000. And this Wilkinson microwave anisotropy probe could actually make a measurement of that. And then this is Planck's satellite. This also made measurements of this small anisotropy. These are very small anisotropies in the background radiation. And that also signifies that in the early universe, everything was not completely isotropic and homogeneous. There were some fluctuations, fluctuations in densities that gave rise to galaxies and clusters of galaxies. So that also agrees with our theories. And another thing I should mention, that if you use powerful telescopes and you look deeper into the universe, you are seeing universe as it existed in the past. And those photographs look different from the galaxies, photographs of galaxies which are close by. So that also shows that galaxies are evolving with time. And the Wilkinson microwave anisotropy also could make some interesting observations of dark matter and dark energy. These are something that we still do not understand completely. There is a lot of matter in the universe which is not visible to any of our telescopes. And actually that dark matter is more than the normal matter that we see around. And there are different theories regarding that. And the idea of dark energy comes from another observation, that the universe is not only expanding, it's expanding with an acceleration. And people don't know why. Usually you expect the speed to decrease because of gravitational attraction between galaxies. And this Wilkinson microwave anisotropy probe could make a measurement of estimates of dark matter and dark energy. So this is the kind of picture that we can draw now. This I have taken from some source. So if you go to the past, if you go to the very early times, see, Weinberg in his book, The First 3 Minutes, says that if you go to very small periods of time, like less than, say, 0.01 second or less than 1/100 second, you cannot tell with confidence what would happen, because that time the density was very high and the temperature was very high, and you don't know with confidence what is the kind of physics that will happen at that time, because physics is an experimental science. When you talk about the behavior of matter at some temperature and density, you should be able to check it with the experiments. So in particle accelerators, people can make beams of particles and let them collide and study. But there is some limit to what you can achieve with accelerators and these studies. So as you go into very small intervals of time, you don't have the support from experimental physics to tell things confidently. And the other thing is that if you go to very small intervals of time, then you cannot just use Einstein's theory of gravity, because at that in small intervals of time or distances, quantum effects also play an important role. So probably you have to develop a quantum theory of gravity to discuss how a Big Bang happened, or whether to ask whether actually a Big Bang happens. But you, from time of the order of, say, milliseconds, you can tell things with confidence. And the early universe, there were a lot of radiation, photons, and also there was a lot of basic leptons and hadrons. Like you had the protons, neutrons, electrons, neutrinos, and their antiparticles. And they got a small, within a few minutes, within 3 minutes, most of the nucleosynthesis already has happened. So hydrogen and the helium and their isotopes and a bit of lithium was created in the first few seconds or minutes. And then due to gravitational force and due to some fluctuations, matter could come together in that took millions of years, and then stars, galaxies, etc. were formed. And there are still things which are not known to us. What is known is that at around 380,000 years, atoms would have got formed by combination of electrons to the nuclei, and the universe would have become transparent, and the cosmic microwave background has escaped. And that is something that you can observe with things like COBE, WMAP, Planck satellite, etc. These could observe that, and with confidence you can tell that this has actually happened, that the Big Bang has the expanding universe is a reality, and it had a very hot, dense beginning. And even before cosmic background radiation, some neutrinos would have escaped, a lot of neutrinos. And neutrinos are very hard to detect, and these are very low energy neutrinos. There's indirect proof that there is a cosmic neutrino background. And this also is in agreement with the current theories. And then stars, galaxies, etc. Formed. And most of the atoms that we are made of, for example, carbon, oxygen, etc., were actually made in stars. We may go to next slide. These are a formation of galaxies, and solar system actually was formed much later. So if the age of the universe is around 13.8 billion years, solar system is only 4.6 billion years, only 1/3 of the total age of the universe. So that is good in some sense, because our body has a lot of atoms like oxygen, carbon, nitrogen, etc. These were not produced in the early Big Bang, but these were produced in big stars that existed much before sun, and they underwent explosions, also mergers, and a lot of interesting things would have happened. And many of the heavy atoms were produced in these cataclysmic events, and all these were brought together by gravity. And when solar system was formed, Earth contained many of these elements, so life could evolve in Earth, and we could all be alive. This is an interesting periodic table. It also shows the origin of each of the chemical elements. You can see from the picture that hydrogen, and helium, and a bit of lithium were produced during Big Bang. The blue color represents fusion at the time of Big Bang. So hydrogen, helium, and lithium were made in that region. Then you can see these green things. That's made in stars. So all the other elements are made either in the usual evolution of stars, or during events like a supernova, or explosion, or merging of neutron stars. So except this beryllium and boron, other elements were made inside the stars. Beryllium and boron was produced mostly by cosmic ray fission, that when cosmic ray particles come from outside and hit our atmospheric gases, many atoms gets broken down, and beryllium, boron, etc. are produced. And let me explain some interesting things. See, for example, you take a look at gold. Okay, this is gold. Atomic number 79. Almost all of the gold was produced in merging neutron stars. This is a very recent observation. First case of neutron merger was observed in 2017, just 3 or 4 years back. This was the first observation using gravitational waves. And this theory has been is now acceptable theory. That is, when two neutron stars merge, there will be a lot of neutrons available, and they can fuse together to produce significant quantities of elements like gold, silver, platinum, which could not be produced in ordinary stars. So if you are wearing a golden bangle or a ring, most of the gold in that was produced in some neutron star merger long back, much before the birth of solar system. Then let me add a few words about the standard model of the elementary particles. When you talk about the early universe, you make calculation assuming standard model of the elementary particles, which was produced by people like Steven Weinberg. So these are the fundamental particles. Material particles, there are two types, leptons and quarks. Leptons, you have electron, and you have the associated neutrino, electron neutrino, and you have three generations of such particles. Just like electron and neutrino, you have a muon and muon neutrino and tau neutrino. These are just like electron and neutrino, but they have a higher mass. And similarly, you have quarks, six types of quarks, UCT, up charm top and down stains bottom, and they are antiparticles. All these leptons and quarks are antiparticles. All the materials that you see around, all the atoms are made of this. And actually, to explain the existence of all the atoms, you need just three particles, up quark, down quark. Together they can produce neutrons and protons, and then electrons. And then you have four fundamental interactions. For electromagnetic interaction, you need photons to explain electromagnetic interaction. Photon are the carriers for electromagnetic interaction. And then for weak interaction, you have three particles, W plus, W minus, and Z particles. And for strong interactions, gluons. Then the standard model also predicted the existence of Higgs boson, which was later found experimentally. And these fundamental forces, people like Steven Weinberg are known for unifying electromagnetic force with weak force. And many people have attempted to unify strong force with these forces, but unfortunately, these have not been successful. These are called the grand unified theories, and they predicted the decay of protons, but experiment did not show decay of protons. So it's an open question whether the strong interaction can be combined with electroweak interaction. And there's a bigger question of whether a gravitational force can be combined with this. And there's a lot of interesting work going on in this field in understanding gravity and quantum gravity. So it's believed that in the very early universe, this is only one force. Then they divided the gravitational force, got separated first, and then strong force dealing with the other, and then electromagnetic force and the weak force dealing. Now we see this as 4 different forces, but probably at the origin, there was only one force. And with this, I'm coming to the end. Thank you. Taranath, my talk is over.
Hello. Okay, sir.
So we can move to some questions if the audience have any questions. I think there are more comments than questions. So can you read this question, Shaji sir?
Yeah, I can read. Which is the first question? No.
After a couple of comments about Schwarzschild and Bethe, then how could Penzias and Wilson ever doubt background noise for microwave radiation?
And is it true that Bethe got Nobel citation for his work on obtaining precisely the fusion reaction core of the sun after his much? Right, you are right, Rajagopalan. Bethe got his work for nucleosynthesis in sun. Yeah, but the time when Gamow put Bethe's name into the alpha beta gamma paper, Bethe was already a well-known scientist. Bethe never claimed that he contributed to alpha beta gamma paper. Bethe was anyway a great scientist, and he got Nobel Prize for something else. How could Penzias and Wilson ever doubt background noise for microwave radiation? Is Earth a good conductor of microwave radiation? Okay. See, Penzias and Wilson were actually analyzing their dish antenna. They were basically physics people, but they were very good in engineering also. So earlier, they actually did a lot of painstaking work. They did a lot of calculations on the possibilities of the noise. The first they thought that is because of some droppings of some birds. So they cleaned the antenna thoroughly, and still they got it. And they could not account for it. And then they thought that it's coming from some terrestrial sources. So they observed it for a long period of time and then ruled out that. Then they thought that there's something coming from sun. But they made observations over several months, and they turned the antenna in different directions, and they could rule out that it's coming from any sources within the solar system. Then they were sort of convinced that it's coming from outside the solar system, and they could make an estimate of the temperature corresponding to this radiation. And then they were informed that already people have predicted this from Big Bang theory. So many others would have missed it, but that's the one difference between ordinary scientists and the great people. So Penzias and Wilson were of the Nobel category. So it was not just accidentally that they got it, they deserved it, the Nobel Prize. Then what is
okay, there's one more question. It's again, can you explain the terms gauge and scalar bosons?
Okay.
It's about gauge and scalar bosons.
Okay, who has asked that question? If it's a student or a teacher. Okay, I'll assume that is a student and answer it. Okay.
It's asked by the same itself.
Okay. But I will answer such that it will be useful to students. Okay. Rajagopal must be knowing the answer, but anyway, I'll answer it. I assume that he wants it to be explained to students. See, electrodynamics is the best example for a gauge theory. You might have heard about Noether's theorem. It says that for every continuous symmetry, there is a conserved quantity. So in electrodynamics, you have different symmetries. For example, it's invariant under lower transformations, rotations, etc. But then it's also invariant under what is called a gauge transformation. You make a transformation, for example, you define scalar and vector potentials. Electric field and magnetic fields can be written in terms of scalar and vector potential. You make certain changes in the scalar and vector potentials that will not affect electric or magnetic field. So, and therefore it will not affect the Maxwell's equations. So that's an interesting symmetry. And corresponding to that symmetry, there's a conserved quantity, and that turns out to be charge. So electric charge is something that is strictly conserved in any interactions. Even if you throw some charges to fire, that will have the charge. Even if you throw some charges into a black hole, it will not get destroyed. The black hole will get charged. So it's a strictly conserved quantity. That's related to gauge invariance. That's called U1 gauge invariance. It's an abelian group. So gauge theory was very successful in electrodynamics. And when QCD was developed, quantum chromodynamics, that's the theory of quarks. People like Gell-Mann and Schick realized that there's a SU3 symmetry, and there's a gauge symmetry is possible there. And you have a gauge invariance there, and you have a gauge theory. It's a non-abelian gauge theory. Now, corresponding to gauge theories, there's a particle source associated with the gauge transformation. In the case of electrodynamics, it's a photon. In the case of weak interaction, you have 3 gauge bosons, 2 charged and 1 neutral. W plus and W minus, these are heavy particles. These were observed in CERN long back, and Z particle just neutral. These are all the best examples of gauge particles. And then in the case of in the case of weak interactions, the W plus and W minus, W plus and Z particles. And in the case of strong interactions, you have what are called gluons, represented by the letter G. Actually, people like Professor Babujas has done a lot of work on those things. So these are gauge bosons. And there's another boson, the Higgs boson. That is not a gauge boson. This is called a scalar boson, and there's a spin 0 particle. The other gauge bosons are all spin 1. W plus W minus Z gluons and photons are spin 1 particles. So this since the spin 0 particles, these are called scalar bosons, the Higgs boson, just like pions. But other particles like gluons, photons, and W plus W minus Z particles are gauge particles. Those are called gauge bosons. Because these are bosons, they are spin 1 particles, and they are carriers of forces. Photons are carriers or messengers of electromagnetic force. Gluons are associated with strong force, and W plus W minus and Z are associated with weak force. I think the answer is clear. Ajobal, sir.
Yeah, I would like to add a question. So what about the conservations of lepton numbers, baryon numbers, and etc.? And what will be the corresponding symmetry associated with those?
Okay, when people proposed the grand unified theories, they proposed that these numbers are not conserved. That's why this led to proton decay, etc. But if you consider electromagnetic interaction, lepton number is strictly conserved. So you can define just like electric charge, you can define something called a leptonic charge. For example, neutrinos do not have any electric charge, but you can say that they have leptonic charge. Quarks have baryon number 1/3. So protons and neutrons have baryon 1. So when whatever particles you observe, they have integer number of baryon number. You can have a quark anti-quark pair, which will have a baryon number 0. You can have a 3 quark system, which has baryon number 1. And recent people have found the pentaquarks, but their baryon number is 1 because they consist of 4 quarks and 1 anti-quark. So for some reasons, the baryon number comes in integers. So that's also a strictly conserved quantity to the best of our knowledge. But grand unified theories demand that these are not conserved.
Okay. Okay. So if there is any further questions?
Yeah, Dr. Shaji, Suresh, see, it would be nice you can tell to students, Weinberg contribution to the development of standard model of particle physics. A little bit you can tell to the students will be nice.
Okay, I will try to explain. I will not be able to give the details. See, if you let me stop this presentation. Okay, fine. See, if you look around, you see a lot of movements. For example, you can see a bird flying, or somebody walking, a child running, etc. Then you can see automobiles moving. So definitely behind all this, there are lots of forces. So first you'll think that there are hundreds or thousands of different types of forces possible. But if you examine deeply, there are only few forces. For example, you look at the movement of electric fan, motor, etc. All these are electric devices, and this can be explained in Maxwell's equations. So you can reduce these to electromagnetic forces. If you look at a bird flying, you can assume that these are able to fly because of their movements of muscles. And if you look into physiology, these are because of motion of charges or inside the cells. So even what we call physiological forces are basically electromagnetic forces. And only other thing that you see around is gravitational force. If somebody falls down, that's a gravitational force. So all the movements that you see around can be explained by electromagnetic force or a gravitational force. But there are some forces which cannot be seen at our length scales, but they are seen only at very microscopic level inside the nuclei or at a very small length scales. These are what are called nuclear forces. One is there are two types of nuclear forces. One is a strong force that binds protons and neutrons together. For example, long back people tried to make gold from lighter elements, and they never succeeded. We know that why they never succeed, because gold is gold because of a certain number of protons in their nucleus, and you cannot do any chemical process to change the number of protons, or you cannot make any change to their nuclei, because these protons and nuclears are held together very strongly. This is called a strong interaction. But you also see things like radioactivity, which can be explained by another force called weak force. And the weak interaction theory was actually developed by people like Professor George Sudarshan and his guide Marshak, and also independently by Gell-Mann and Feynman. And the electromagnetic theory was developed by Maxwell. Maxwell used the work of a lot of others and they put together. And they have the quantum theory of electrodynamics. It's called the quantum electrodynamics. That's the best theory that we have around, because if you make predictions with electrodynamics and that agrees with the experiment to say 11, 12, or 13 or 14 decimal places. So that's the best theory we have around. And for weak interactions also, you have this V minus A theory. And people like Weinberg, then Glashow and Salam, they all developed a theory which put together electromagnetic theory and weak interaction. So in a sense, you can say that from a single theory, you can explain both these interactions. So if you usually you do this in terms of what is called a Lagrangian. Lagrange's method is a method which is better than Newton's approach to classical mechanics. You define kinetic energy, Lagrangian as difference between kinetic energy and potential energy. Kinetic energy minus potential energy is the Lagrangian, if you write in terms of generalized coordinates, etc. So in a sense that they could write a Lagrangian density, the Lagrangian, which will describe both these interactions, weak interaction and electromagnetic interaction. And that was developed as a gauge theory. See, for these theories, anybody can make a new theory, but if you expect people to accept it, it should be able to predict something, and it should be able to explain things. So this theory of Glashow-Weinberg-Salam, they predicted certain things. One was the existence of W and Z particles, which were later found in CERN experiments. And there is something called neutral decay of particles, which involves Z0 particles, which was actually discovered even before the Z0 particles. So particle interactions, if you observe, there's something called neutral currents. This was another prediction of this theory. Then there were other theoretical developments, like if you have field theories, there is something called renormalizability. That is, usually when you make calculations, infinities come up. And there is a systematic way of removing these infinities and getting finite results. That's called renormalization. And some other people like Tooft and Weltman, they actually showed that this electroweak theory is renormalizable. They've actually got Nobel Prize for that. That was a big boost to Weinberg-Salam model. And then there was Higgs had predicted existence of Higgs bosons, and Higgs theory was essential to the essential gradient to this Glashow-Weinberg-Salam model that was detected in CERN Large Hadron Collider experiments. So the present status is that it is a very well accepted theory. Now people are trying to go beyond the standard model. There were some experimental results on magnetic moment of muons. That's called J-2 anomaly. And the people suspect that you may have to go beyond the standard model to explain certain things with accuracy. These are the basic things about Weinberg-Salam model. I cannot go into further details. Suresh, is it okay?
Yeah, fine.
Maybe you can add something, because many of these people are experts in this, I know.
Maybe we listen some question from students. So then, yeah.
You can either type in the question or ask directly.
Yeah. Yes, there are only very few people here. You can unmute yourself and you can ask.
Sir, I'm Rajagopal. Your comment on scalar bosons and the chapter 8 of 8 in quantum field theory by Ryder. Do you think that is the most helpful? That is the thing I read long before on this subject.
Yeah, Ryder is a good book. There are many other books also.
Sir, can you hear me?
Yes, I can hear.
My question was clear.
Yeah.
Better. The reference, like, is there any this is good enough, but do you think there can be better references also?
See, you can see any of these references, but you have to sort of sit down and work out things. You have to spend some time to understand these things if you want to get a real understanding of it.
Thanks.
So, is there any further questions? If not, we can wind it up. Manu, sorry.
Okay, thank you, Shaji sir. And as Tarnath already mentioned, there's no better option than Shaji sir to discuss the works of Weinberg. Thank you very much, Shaji sir, for this very clear, simple, and powerful talk. Thank you so much, sir. And once again, let's wholeheartedly thank Professor Babu Joseph, the renowned theoretical physicist and writer. Babu sir is Kuriakosa's guide, and we had no better choice than Babu sir to inaugurate this workshop in memory of Kuriakosa. Sincere thanks to you, dear Babu sir. And on behalf of VCK sir students and each and everyone present here, once again, let me thank our resource persons Professor Ajit Kembave and our dear Shaji sir, and many of the former and present faculty members from CUSAT and colleagues and collaborators of Kuryakos sir was with us, I must say was. And thank you, dear teachers and friends. And we acknowledge the presence of Kuryakos sir's wife, Lilama teacher. Special thanks and best wishes to all the participants of this event. And it's Kuryakos sir's students who all work together effectively and efficiently to materialize this workshop, especially Nijo, Taranad, and Jishnu. Okay. And once again, sincere thanks to all those who participated in this webinar conducted in memory of Professor VC Kuryakos. Thank you. Thank you all.
The meeting is over now.
Yes, we can leave now.
Yes, sir. Yes, sir. Thank you.
Thank you. Thank you all.
We feel very much honored by your effort in conducting the seminar all these years. Thank you all.
It's our privilege, teacher. It's because of Kuryakos sir only we are all here. We know it very well now.
ടീച്ചറെ സുഖമായിട്ടിരിക്കണോ? സുരേഷാണ്.
സുഖമായിട്ടിരിക്കുന്നു. കൊച്ചുമക്കളൊക്കെ ഇവിടെ ഉണ്ട്, അതുകൊണ്ട് തിരക്ക്, അതായത് ബഹളവാ. ആരും സാറിന്റെ ഫാമിലിയിൽ നിന്നും ആർക്കും വരാൻ പറ്റിയില്ല. ഇന്നലെ ആയിരുന്നു നിങ്ങളുടെ പള്ളിയിലെ സർവീസും കാര്യങ്ങളൊക്കെ. ലോക്ക്ഡൌണൊക്കെ ആയതുകൊണ്ട് എല്ലാവരും സുഖമായിരിക്കുന്നല്ലോ.
വീട്ടിലുണ്ടോ ടീച്ചറെ? മനോജൊക്കെ വീട്ടിലുണ്ടോ? അതെ പോയോ?
എല്ലാരും ഉണ്ട്, എല്ലാരും ഉണ്ട്.
അവർക്ക് വർക്കിംഗ് ഡേ ആണല്ലോ.
വളരെ സന്തോഷം.
സജീത്തിന്റെ പുതിയ ഗവേഷണങ്ങളും കണ്ടുപിടുത്തങ്ങളും ഒക്കെ എനിക്കൊന്നും മനസ്സിലാകുന്നുമില്ല, പക്ഷെ അറിയുന്നുണ്ടൊക്കെ, വായിക്കുന്നുണ്ട്. അതിനിടയ്ക്ക് ഈയിടെ അറിയുന്ന സജിത്ത് ഭയങ്കര എഴുത്തുകാരനാണെന്നും. അല്ലല്ല, അതൊരു വലിയ ഇതാ. ഫേസ്ബുക്കിലൊക്കെ ഇടുന്നോണ്ട് ഞങ്ങൾക്ക് വായിക്കാൻ പറ്റുന്നുണ്ട്. താരാനാഥും അങ്ങനെ. താരാനാഥ് ദിവസം ഓരോ കവിത എഴുതുന്നത്.
പാർട്ടിസിപ്പൻസ് പോയെങ്കിൽ നമുക്ക് വേണമെങ്കിൽ നമ്മളെല്ലാവരും വീഡിയോ ഓണാക്കിയ ഗ്രൂപ്പ് ഫോട്ടോ എടുക്കാം അല്ലേ? പക്ഷേ
സ്ട്രീമിംഗ് ഒന്ന് സ്റ്റോപ്പ് ചെയ്യുന്നത് നന്നായിരിക്കും.
സ്ട്രീമിംഗ് സ്റ്റോപ്പ് ചെയ്യാൻ